No, this is either.
Oh, right. See, the building is locked.
Yes, that's the problem.
Yeah.
You have to wait someone to let you in.
Yeah, exactly.
The front door's open actually.
That door is
Yeah,
open?
that is
Oh, okay.
open.
The main entrance is closed, like for...
Oh, really? Okay. Nobody, we just came in here.
Yeah.
So we wait like 9:05 or...
Yes, we do.
Yeah.
So everyone has to wear a microphone.
Ah, okay.
Just to make sure.
Okay. Maybe you can start, right?
Ah, yeah, that's actually.
What do you want me to do?
With a microphone.
Yeah.
Test. Oh yeah, it works.
So it's already turned on? Or?
It's on.
So, but I sit down again.
Yes,
right?
yes, it's 2 more minutes and... Yes, I think we can start. Yes. All right. Welcome to the second day of our ITAMP workshop on unraveling many body physics with on-range interactions. So our first speaker is going to be Andreas Hemmerich. He's going to talk about dissipative time crystals in an atom cavity system.
So, good morning, everybody. Is the microphone working well? Okay. Yeah, I also want to start with thanking all the organizers, Stefan and all the others, for, well, putting this interesting workshop together and having me here and giving me the chance to be in this nice place again, and seeing many people I know, and yeah, thanks a lot. So I will talk about dissipative time crystals in an atom cavity system. And before I do that, I want to introduce my collaborators on this. We have wonderful theory support in-house by Ludwig Mattei's group, together with his graduate student, Jeppe Schulte. And there's also Jason Cosme, a theorist who's with the University of the Philippines. And this is the experimental team. There's Hans Kessler, who's a senior postdoc. And most of what I talk about is his work, actually. And there's graduate student Fatamon Konkambuj and a master student, Sahana Rao. So if you put time crystals into Google, this is what you get. And if you take a look at that, you might wonder, why is it that the most fancy graphic art comes from esteemed, serious, well, physics platforms like Physics World or Nature or Scientific American, as compared to entertainment industry outlets. Well, it seems like that somebody wants to tell us that time crystals, that's something really strange, awkward, mysterious, but actually it's not. Well, let me invest a few words to, well, address that issue and make you believe that it's not at all awkward. So let's start with something we all know. Crystals. Well, to understand time crystals, why not start with crystals in space? And you know that if there's water and you turn it into ice, there's a phase transition, which is connected to spontaneous breaking of spatial translation symmetry, in the sense that if you look at a single atom, its position is completely random and determined by thermal or quantum fluctuations. Whereas the distance between neighboring atoms, that is something that's pretty well fixed by the lattice constant. And this is a constant that is pretty robust against parameter changes like temperature or pressure and so on. So, and then at some point, the question has arisen for some people whether there's something analogous in time. And that has led Frank Wilczek, whom you know from, well, other kinds of physics, not time crystals, to ask that same question. Is it possible that you have a closed system in the ground state or in a thermal equilibrium such that there is an observable A that oscillates at an intrinsic system frequency, and there is continuous time translation symmetry spontaneously broken? That's the kind of proposal made in this paper. And people have started looking for these kind of things, but pretty soon, didn't take all that long, 2015, a paper turned out saying that this is impossible. However, instead of giving up, many physicists believe that this is too a good idea to just well, get rid of it, and well, that it's maybe better to, well, kind of broaden your horizon and make the system a little bigger and see how big, what do you have to add to make it possible. And this has led to the notion of discrete time crystals. And the idea is that you add a drive, an AC drive, that, basically takes care that continuous time translation symmetry is already broken by the drive. And that drive is connected to the system A. And then the idea is that after initial switch-on phase, you have zero energy transfer average over a driving period between the drive and the system. No entropy is generated. And the system answers with an oscillation at a frequency that differs from any multiple of the driving frequency. So there's a kind of a period doubling dynamics happening. And then, in that sense, the discrete time translation symmetry introduced by the drive is broken. Yeah. And then pretty soon, a number of people have engaged in showing that something like that should really be possible. For instance, Christoph Sascha from Krakow and a couple of other groups. And not long after, there has been the magic year 2017 with this Nature cover, and celebrating two experiments that have shown that this is possible. One from the Monroe Group in Maryland, and another one from Looking Group here at Harvard. And this then has triggered a discussion on what are the accepted criteria of a time crystal. When is a time crystal a time crystal? You see already the discussion was cooking high. And this is a kind of collection of what has been, what is believed to be the minimum selection of properties that a time crystal should have. It should be a driven, closed, interacting many-body system. So we are not talking about classical physics. There should be an oscillation at an intrinsic frequency incommensurate with the driving frequency. And there should be a spontaneous breaking of the discrete time translation symmetry, and there should be robustness with respect to changes of the system parameters, noise of the drive, and system noise. Okay, so then there's a challenge in all that, and this is to prevent undesired heating due to dissipation, which typically destabilizes the oscillation and leads to melting of the time crystal. And this again has then brought up a new chapter of the discussion, whether we cannot possibly engineer dissipation in a way to stabilize rather than melt time crystal dynamics. And again, theorists have occupied themselves with discussing whether that's possible or not, and the answer turned out to be positive. There's these first papers discussing that, but there are other ones as well now. And also, theorists have discussed then soon that in open systems, if you allow for dissipation, driving may be continuous even rather than periodic. So this leads again back to the idea of a time crystal that breaks continuous time translation symmetry. So that basically leads us to these two possible scenarios. We have our system now, we have a bath, we have some designed dissipation, and we have a drive. There is net energy transfer from the drive via the system to the bath. However, no entropy is generated in the system. So what flows in flows out, and this has been called a discrete dissipative time crystal. And as I said, also that is possible, that you work with a DC drive. So your drive preserves time translation symmetry. Again, there's net energy transfer. from the drive via the system to the bath, and no entropy is generated in the system. And in this case, the system simply provides an observable that is oscillatory. And the dissipation stabilizes this oscillation. And this has been called a continuous time crystal.
Yes, just a question. What do you mean by DC drive? Is it just a static field? Or?
Well, this is a laser beam that's not modulated, in our case.
Some constant coupling.
Some constant coupling, yeah. So it could be, it depends I mean, there are all sorts of very different systems. It could be an electric field that's constant. It could be a force, a phase difference, something like in Josephson effect, you have a phase difference, something like that.
In the end, if normal is completely classical, then, right?
Yeah, right. Yeah. Well, depending on what system you take, but you can find classical systems easily.
But
Yeah.
in a purely quantum system without dissipation, there is no time crystal. Is that the conclusion?
Well, there's what people have called discrete time crystals. This is it doesn't require dissipation.
It requires many-body localization.
That has been discussed as one mechanism to, yeah? Yes. But that would be not classical, right?
Sure, but there are doubts about many-body localization too.
Yeah, yeah, that's another discussion now, whether it exists. Yes. But that's not my topic.
Yes, okay.
Yeah. Okay. So that's my outline. Now I come to the physics that I understand things, and so that's a happy harbor for me. So I show you the Hamburg atom cavity system, and then I'm going through these three topics: realization of a discrete dissipative time crystal, realization of a continuous dissipative time crystal. And then, once there's a continuous dissipative time crystal, you can seed this time crystal in order to go back to a discrete time crystal. That's what I will show you. So that's our cavity setup in short. There's simply two mirrors, and we have a Bose-Einstein condensate in between. The atoms act to shape the photon state, and vice versa, the photons act to shape the atomic state. I have written here what's the role of the cavity. For people who don't want to go into details, photon storage increases the atom-light coupling. This is what the mirrors do for us. But also we have multiple scattering of photons, which mediates an infinite range interaction between the atoms. And this is probably the reason why I'm here, that there's otherwise, well, you know. And there's a long photon lifetime in our setup that leads to retardation of the infinite range interaction. That's kind of a unique point about our cavity setup as compared to other ones. Yeah, from a many-body viewpoint, in a single sentence, photons mediate strong retarded infinite range interaction between the atoms. I don't know, do I stand in the way here? I could go a little to the back. Okay, so this is our cavity. You see that this is a kind of macroscopic device. The mirrors are 50 millimeters apart, 5 centimeters. This is the Bose condensate, not to scale. And these are a few numbers for the ones who are, well, want to know a little more than what I was showing before. The finesse of this resonator is 420,000. There's a Purcell factor. This is basically the single atom cooperativity, which is fairly high, 44. And we have a bandwidth, and this is important, kappa divided by 2 pi, which is only 3.4 kilohertz. And this has to be compared with the recoil frequency, that's 3.6 kilohertz. So we are in the recoil resolved regime, which means that the motion of the atoms to adjust to a change of the field, of the photon field at the cavity, that motion goes with the recoil frequency, and this is on the same order as our lifetime of the photons in the cavity. So that's a peculiar situation where your long-range interaction is retarded. It's not instantaneously reacting to a change of the cavity field. So there's a paradigmatic pumping scheme that many of these cavity experiments have used, which is actually fairly old. It has been proposed by Peter Dommerkosch and Helmut Ritsch, and already 2002, a long time ago. And then it has been applied even in cavities, real cavities with real atoms by Vladan Vulicic's group. I'm sorry that he's not here. I would have loved to see him smile when I say that. This is 2003 with, however, with thermal atoms, laser-cooled thermal atoms. And already in this experiment they have observed something that's been called self-organization phase transition with thermal atoms in this case. And later on, a couple of years, 2010, the first experimental demonstration with condensed bosons has been demonstrated by the ETH group, and it has been argued that the self-organization phase transition in this regime, when you use a Bose condensate, can be mapped to the Heppley phase transition in the open Dicker model. So that was a progress in terms of interpretation, and then in 2015 we had everything together to have a BEC in a recoil resolved cavity. So this is a short view at the signatures of the self-organization phase transition, because we need to know that for what comes later. Tilman Esslinger is not there anymore. He has basically prepared all what I'm showing here and talked about it, but nevertheless I go through it quickly. So this is our scenario. We have a pump wave, and the atoms are, well, basically the atoms in a Bose condensate, and along the cavity axis they are sitting at random positions, and this is why there's practically no scattering possible. And well, why is that? Because every atom has a neighbor atom, lambda over 2 away, that, well, scatters with opposite phase. So there's always destructive interference between different kinds of atoms. However, if you go strong enough with a pump wave, then, well, you go through a phase boundary into a situation when all of a sudden the scattering works. The atoms are reorganized spatially into a checkerboard lattice such that the Bragg condition for scattering is perfectly fulfilled, and very efficient scattering of photons into the cavity sets in. And you see that because there's some photons leaking out of the cavity. And you also see that by the fact that starting from here, this is kind of a scheme of the momentum spectrum where you have plus minus 2 h bar k peaks here and here due to the standing wave of the pump field. And now you get extra Bragg peaks that show you that you have this kind of checkerboard lattice configuration. Okay, so that's that.
Do you mean by superradiant phase here?
Well, superradiant phase, that is, well, there are different kinds of names that have been used, like self-organization phase transition or superradiant phase transition, because the superradiance just means that the atoms are organized spatially in a way to perfectly scatter photons into the cavity. So in some sense, I mean, we could discuss that, whether that's the best possible name, but that's what's meant by superradiance here, right? Coherent scattering. No, typically not. The cavity is many nanometers detuned from the atomic resonances. So we are working in the dispersive regime, and spontaneous photons practically don't exist in our experiment. So you can say the atoms in the Bose condensate are basically some droplet of matter that has an index of refraction. That's what it is. Okay, so now I show you briefly what happens in the experiment if you go through the phase transition. Well, you can draw a phase diagram like that, and I don't want to get into the details. Some people will know this anyway by heart after hearing it a few times. So below this line, this is where the normal phase, NP, prevails. This is the calculated critical pump strength. Above that, we should get into this phase here. You see that this is not quite true. One has to go further into this region before you start seeing photons in the cavity. The color code shows you the amount of photons coming out of the cavity. And if you are here, for instance, inside this superradiant phase, then you can see these extra Bragg peaks that tell you that there's a checkerboard lattice available now. Okay, so this is some interesting feature here that it seems like this equilibrium phase boundary is not correct, but actually it is correct. The point is that since we are getting this picture by ramping from 0 towards higher and higher pump strengths, and crossing this line, is sort of associated with retardation, and that is seen in this picture here. So you see what happens if you go in to the superradiant phase, the blue line here. It takes a while before the system realizes I'm in the superradiant phase, and then it adjusts to go back to where it should be, and the way back you go along the red curve. So that's the kind of retardation that I've been talking about before. There's one important point associated with this transition. This is the fact that there's a Z2 symmetry breaking, which will be important later on as well, which means that there are two lattices actually that can self-organize, which are shifted with respect to each other by half an optical wavelength. It's the green and the blue lattice that I'm showing here, and you can also say that these are the two possible white and dark fields of a checkerboard that can be populated by atoms. And this means in this case here and in this case, you have different relative phase values with respect to the pump wave, which you can observe by looking at the light coming out of the cavity with the heterodyne detector. So this is done here. You see what happens. We are starting in the superradiant phase. This is the photon level inside the cavity. So the light leaking out of the cavity has a certain phase, which is 0 here in this case. Then we are going back to the normal phase. There's no light in the cavity here. So the heterodyne detector goes wild because it doesn't get a signal. And then at some point we are returning back, we are going up again, and you see again we're ending in the superradiant phase with a phase value that is 0 as well. But in every other case, instead of getting phase 0 here, you get phase pi here. So there's a spontaneous picking of the phase for once you go through this phase boundary. And this is a histogram showing you how often which phase is picked, and it's pretty much 1-to-1 in our experiment. So now we are set for the realization of a discrete dissipative time crystal. And what we do now is, well, we apply amplitude modulation to the pump in the superradiant phase. So basically what we do is modulating these pump waves according to this, this formula. And well, the frequencies are typically on the order of a couple of kilohertz, and the modulation indices, the strength of the modulation is somewhere between 0 and 1. And this is in one plot what happens. So this shows you the intercavity, the pump wave, basically the pump strengths. This is this y-axis here. And here you see that the pump strength is basically linearly ramped up until some point here. Then it's kept constant for a while, and then the modulation is started. And here you see how the system reacts. So there are two signals. The red signal is the intercavity photon number. So you see here it's 0. Once you go to this point here, where the dashed line is about, you're entering the superradiant phase. So light comes out of the cavity, and then we are ramping up further to here, and the modulation starts. And immediately the system reacts by an oscillation of the intercavity photon number that well, is the same at the same frequency as the drive. However, if you look at the phase, then you see that there's a period doubling occurring. So if we're now looking at what the atoms do, we can also see this very nicely. Well, we start here. We are in the normal phase still at this point, no light in the cavity. Here we are already in the superradiant phase with these extra Bragg peaks. And you also see a calculation for this momentum spectrum. Sorry, why does that happen? Which shows the single particle density pattern of the atoms. And now at this point, I'm showing you 3 instances of time where at this point we are, I'm talking about this point here, we are in this situation. Just a second, is there, yeah, this belongs to the peak of the intercavity photon number here. So we are in the situation now where we have a checkerboard structure which corresponds to this calculation here. And then the next instance of time, the photon number is down to 0, which corresponds to this spectrum here. And you see that there's basically a standing wave along the pump direction now, and no checkerboard geometry. And if we go further to the next maximum, then we are not back to this case, but we are going to the other symmetry broken lattice configuration, where now the lattice has shifted by half an optical wavelength. Okay, so that's that, and this shows you briefly that again we can make visible the spontaneous breaking of the Z2 symmetry connected with this transition. I don't want to go to the details here. And this is showing you a phase diagram where I'm plotting the modulation frequency on the x-axis and the modulation strength on the y-axis. And there's an island where these dynamical state lives. And what's plotted here is what we and other people have called the crystalline fraction. So if you take an FFT of the signal that we're looking at, the light that's leaking out of the cavity, and you plot the size of the peak that you find if there's time crystal oscillation, then you get this kind of picture here. So everywhere in this island there's a certain amplitude, that's the fraction of the atoms that contribute to this self-organized oscillation, the time crystal dynamics. Okay. yeah, then we can look a little bit in this phase diagram at different places. Now for this picture we are here at this point, and you see that there is no oscillation whatsoever. This is the FFT, and you see this has basically a flat power density. So here we are basically in the superradiant phase with no oscillation. So let's move up with where we look. So now we are at this point here, and well, you can see that now you have this period doubling and oscillating phase, and you have a very nice FFT peak at the frequency which is half the driving frequency. And if we go on, for instance, to here, we are seeing these kind of pictures where, again, the oscillation is kind of irregular and closer to the driving than to half of the driving frequency, and we do not see much of a peak structure in the FFT. So I told you that for time crystals you want a certain amount of robustness, and we've looked at that. So what we've done here is to add noise to the drive. So this is the drive without noise, and now we're starting to add noise more and more. B, C, D you cannot easily recognize anymore that you have a defined driving frequency. And you see that you can apply quite some noise before the system starts to become irregular in terms of the oscillation that you see. And this can also be plotted by plotting the relative crystalline fraction again against some parameter that well measures the strength of the noise that you have applied. And you see there's some kind of, if you want, some kind of plateau, and then it goes down to some low number, and there's no time crystal dynamics anymore. But it requires a significant amount of noise. And what you can also do is do some calculations using truncated Wigner approximation calculations. This is what is done here, and I'm looking at different cases where I'm adding binary collisions. So now the first, the blue oscillation is without collisional energy. EC is 0. Gamma is a loss rate that we've pretty much put in by hand to simulate what happens if atoms get lost. And you see that, well, this is just ordinary time crystalline dynamics, and if you add a little bit of binary collision, then nothing much happens. The green curve is pretty much the same as the blue. Now we are at 0.08 recoil energies for the energy, the collision energy per atom. And even it seems like for the red curve, you're already at 0.3 recoil energies, collision energy, you still see this oscillation, but then it kind of drops to this different amplitude here, and actually the coherence gets lost. It's hard to see from this, but this is actually irregular already to a degree that you have practically no coherence anymore. Yes, and this is seen here.
5 minutes include for the question time, so.
Yeah, do I get the 5 minutes back that I started later?
It's already passed,
Huh?
already passed the 3 minutes, so.
Yeah, okay, okay. I try to be fast. Okay. So that's time to switch for the realization of continuous dissipative time crystal, and well, in that case, we are looking at a situation where we have anomalous dispersion. So our pump wave is now blue detuned with respect to the atomic resonance, and this means that the atomic refractive index is smaller than 1. And well, in that case, the dynamics is different than for the red-detuned case that we've seen so far. I don't want to go into that. You can basically say that new situation doesn't allow a simple steady state where you form a lattice, a stable lattice in the resonator. Well, you can say that if you have atoms, if you have photons in the pump coming in and atoms are around, then you can scatter, and this scattering yields an intercavity lattice. But now the atoms move away from the intensity maxima towards the intensity minima, and this means the atoms, well, stop scattering, and if they stop scattering, the intercavity density gradient collapses, and this kind of makes an unstable situation, and the system starts an oscillation. It's not quite that simple, actually, but forgive me for trying to be fast on that. So, yeah, one can do simple calculations doing mean field with quite a few modes taken into account. We are taking 5 times 5 momentum modes into consideration here. And then you see that, in fact, there's a region in this phase diagram where we see these stripes. This is the oscillatory region around where I put a 2 here. Here, things look more chaotic, and at this place here, you seem to have no oscillations, but rather a kind of a superradiant, stable superradiant phase. And this is also, well, confirmed by looking at the frequency that the system emits with an FFT. And you see at 2, there's a nice FFT peak. At 3, there's nothing. There's no oscillation. So this is the superradiant type of phase that we've also seen for red detuning. And in the chaotic region, you see things like that here. And you can plot the frequency that the system chooses to oscillate with. And you see in this island where this time crystal behavior prevails, there's pretty much the same frequency everywhere around 10 to 11 kilohertz, something like that. And these are calculations, again, truncated Wigner approximation calculations where different TWA trajectories are calculated. And you see they come with different phases. So everyone picks randomly a different phase, and this you can plot like that. So I see you standing up already, so I have to move,
Yes.
right? Okay. So yeah, here very briefly in the experiment, how much time do I have? Do I have 3 minutes or?
Well,
No.
no, like
No.
one.
Like 1 minute, okay. So now we are looking at the experiment, and we see this oscillation, and there's a peak here. And if we look at the phase distribution, in fact, it looks like that every phase is equally probable, and everything is like theory predicts. And this, I'm getting around that. This is a phase diagram, and this as well. I don't have time. Robustness, again, no problem. We can add noise and don't disturb the system all that much. And at the end, I still have 2 transparencies for seeding. So now what we're doing is, in the phase diagram, we go to this point. And what you see is this is kind of the free-running continuous time crystal with full width at half maximum, which is 270 hertz. And if we now modulate with 22.5 kilohertz, we bring the system to emit a more narrow emission at exactly half of that frequency. So there's, again, this period doubling business. It's like if you inject a laser. You get mode pulling, and you can make the laser that's non-ejected, you can make that more narrow bandwidths. You can, well, have a more narrow bandwidth of the injected laser. And you can see this here in the data, like this is the response frequency in units of the drive frequency. And you see that at the right modulation strengths, you get very sharp lines where the error bars are not even seen because the symbol is larger. Okay? So, so now I have to stop. I'm sorry for that. One sentence, this shows us that if we do the injection, we are going back to the C2 symmetry. You see the phase are in the right positions for this C2 symmetry. Sorry. Wish list for later. What next? And it would be nice to have time crystal dynamics in strong correlated regimes. It would be super nice if the quantity oscillating would be a correlator or an entanglement with this rather than expectation value of quasi-classical observables. And why not dreaming of a time crystal oscillating between a superfluid and a mod insulator? That's the kind of thing where one could want to go to. Okay.
Great. We have time for one quick question.
Yeah, I have a question. So maybe coming back to this discussion before, with like how quantum is it important for the physics you're seeing, in particular for the continuous one, that you have a BC? So is the coherence of your atoms actually playing a role, or if you now heat up your system, for example, how long would similar dynamics prevail?
Well, we cannot afford to heat up much. Well, the question is on what level are you asking? So if you want me to prove theoretically that you need so and so much coherence of your BEC, well, actually we need definitely a situation where we are RICO resolved. Otherwise, it doesn't work. So the BC has doesn't. If it's not yet a BC, it has to be a sub-RICO temperature. So that's the minimum that's needed.
Perfect. So we have to wrap up now, and we are going to move to Zoom. Unfortunately, our next speaker could not make it. So. Great. All right. So we have Francisco there. Hello.
So Francesco, can you hear us?
Yes, can you hear me?
Yes, perfect.
Good.
You can share your screen.
Yeah.
Okay, great. Okay, so our next speaker is going to be Francesco Piazza, and he's going to tell us about the peculiarities of photon-mediated interactions and their effect on the Fermi surface. Francisco.
Yes, thanks a lot again to the organizers for inviting me. I'm really sorry I couldn't come, and I'm grateful also for the opportunity of giving this talk online, and at least I could listen to Andrea's talk, which was also the perfect introduction for my talk. I will also discuss cavity-mediated interaction in like not stationary states, but in ground state, let's say, or like equilibrium state, and not for bosons, but for fermionic matter. So let me go to the outline. So first of all, I would like to introduce a system where we realize this cavity-mediated interaction between fermions, and then I will split it. The first part will deal with the static part of the cavity-mediated interaction, which is already peculiar and aligns with the topic of this workshop because it is a very long range, actually naturally infinite range interaction, but it is an oscillating interaction, so it has a very sharp momentum structure and finite Q in terms of the transfer momentum. And this structure will allow us to solve the competition problem between different ordering phenomena exactly, let's say, and will lead to interesting forms of conformational pairing. In the final part of the talk, I will switch gears and go to the dynamical part of the interaction, which due to another peculiarity of the cavity-mediated interaction, exactly the fact that the cavity has a very well-defined energy or resonance, makes the dynamical component of the interaction very important in many cases. And I will show how this can modify yet again the nature of the interaction and make even the role of the quantum state of light of the mediator of the interaction important. So, two slides about the models. So we start by the fact that we consider how light couples to matter in the standard way, this non-relativistic minimal coupling that everybody knows, where we have electrons here in the psi, and we have the standard vector potential. And we want to couple these photons to a Fermi surface, so we want a finite density of quantum degenerate matter, and for instance electrons in a solid, in order to make the coupling to light, or make the light-mediator interaction, even in vacuum, we need to do something so that the quantum nature of light becomes important. So even zero or few photons can affect the matter. And to do that, we need to confine the light, which is done typically using cavities. And if you do it, for instance, putting a solid inside a cavity, you get a coupling between photons, which have modes enabled by Q, to the electron current, which is, if you want, the lattice version of this minimal coupling P dot A, and the electron current is defined this way. And this realizes really a new regime, if you want, of the high energy quantum electrodynamics. It moves it to low energy, finite density of matter, and potentially due to the confinement strong coupling. There is another category of quantum matter that you can couple to cavity and therefore use cavity-mediated interaction with a Fermi surface, which are ultra-cold atoms, ultra-cold Fermi gases, again within a cavity. And coupled to the motional degree of atoms, many of you know that you need to use the dispersing coupling that Andreas already discussed, which couples then, let's say, photons now to the density of the atoms. So not the current of the electrons, like in solids, but to the density of the atoms. And both are interesting and relevant. There are many ongoing experiments in both cases. Let me start with the ultra-cold atoms. We have heard in the talk of Andreas that this is quite well established, this type of coupling between light and matter for ultra-cold bosons. There are also now experiments with fermions, I guess roughly since 2020. And in solid state, there are also several experiments, and I want to make a comment that maybe you have some question about later. The fact that in solid state to reach really the quantum PVD regime is more difficult, and you need typically very strong compression factors, because if you take just the volume of the cavity, which has a size of the order of the wavelength of the light, then the scale of the coupling, G0, is like 0.1 the Hoping, like in a solid. So it's like tendentially a small quantity, but even in this small coupling regime, it seems that the cavity can do a lot to a material. There's been experiments very recently that show that you can move changing critical temperatures for like transitions in a solid by like 50 or 100% just putting the solid in a vacuum of the cavity. We can discuss this, but now let me switch gears and concentrate on a particular version of actually this type of coupling to the right. And which is, let's say, we consider a single mode cavity, let's say a standing wave, which has a characteristic wave vector Q0 in this direction, like this are supposed to be the mirrors, the Fermi surface, and there is this Q0 in this direction. So now the single cavity mode couples with a strength G to the Q0 or Q0 component of the nest defined in the standard way. Now, if you look at this is similar to like coming from solid states to the coupling between electrons and phonons rather than coupling to electrons and photons, because we couple to the density and not to the current. But there are differences like the infinite range, and or if you want, the fact that you couple very sharply to a single momentum component of the density. This type of coupling, which I just told you is not natural for electrons, it can be engineered also for electrons, again, using two photon transitions like has been proposed, not yet realized. And just to justify that, I will concentrate basically in all the rest of this talk on this type of coupling to the density, and it's natural for ultra-cold atoms, but I will call it general light matter coupling, with having in mind that it can also be realized in solid in a different maybe regime of parameters, but still I want to make a claim that is even more general than just ultra-cold atoms. Maybe I can stop here for a second if there are questions about model, and if you can follow this part so far. Okay, you can interact with course. I interact later. And what I want to do now, sorry, yeah?
All good.
All good, all good.
Yeah.
Oh, good. So I go. Yeah, so as I anticipated in the outline, I want to start by looking at the static component of the interaction, which means, the static component, that's the first part of the talk. So I take this model and I do the static approximation where I eliminate the cavity, the mode, the mediator, in the static approximation, also called the adiabatic approximation, meaning that the characteristic, the tuning of the cavity or frequency of the cavity that Andreas talked about becomes much larger than all relevant scales in a way that actually I will define more precisely later. And this trivially leads to a coupling which is, again, density, the same density component to the square of the coupling between metal and light, the usual elimination divided by this frequency scale or the tuning delta system. So this is very standard. So let's see what this does. So very naturally, we see that this type of interaction, being a density-density interaction with this Q0 component, favors the creation of a density modulation with this Q0, which is this ordered parameter here, which I call here charge density wave, that is nothing else of the fermionic version of what Andreas just told us, and he called it self-organization transition or superradial transition. And this happens if this effective interaction is attractive on this side, and you go beyond a certain strength of this attractive coupling. And this is also as a function of temperature. It becomes more difficult to do it at higher temperature. So these first thermal experiments were like here, and the ultra-cold experiment are more like here, but this continues to be connected, and that's the physics of this charge density wave. And this is the most natural kind of transition that you can have in these systems. And now my question is, okay, these are the experiments. I should tell you that the experiments that Andreas mentioned for bosons are now being done observing this charge density wave or superradial transition also for fermions. It essentially works the way as very nicely Andreas introduced for me, and all works as expected. But the fact that we have a Fermi surface, of course, adds a few interesting features. I would like to mention one, which I think is very interesting, which is the fact that if you put yourself at the superradial or charge density wave transition here, and you look at the critical behavior, you see that at the critical point, the fluctuations of the electromagnetic field in the cavity become so strong that they can destroy the electronic or the fermionic quasi-particles around the Fermi surface, leading to this so-called non-fermionic behavior. In this case, characterized by a decay or quasi-particle damping that it becomes dominant at low frequency, which is characteristic exponent 2/3. And I think this is the first thing that you can say what changes if you have a Fermi surface. You can look at these kind of quasi-particle properties here and what happens around the Fermi surface. And I should comment that to have actually this destruction of quasi-particles, you need to go away from the single mode cavity more to a multi-mode cavity like the ones realized in the experimental plan lab Stanford, where you have many modes and you need a continuum of modes to destroy the quasi-particles, but it's the same kind of superradiant or charge density wave transition criticality that makes this possible. But this is like a parenthesis, so let me go back to my single mode case. and ask the following question. We experiments even have already seen that this charge density wave exists also for fermions, actually. And my question is, what happens in the rest of the phase diagram? Are other orders that compete with this? And the first observation is that we can take our effective static interaction mediated by the cavity that I wrote in this way and rewrite it back in terms of fermionic creation and destruction operators. And this charge density wave order parameter corresponds to taking this fermion bilinear CW field, like in the way I defined it before. But actually there are other bilinears that you can take, and you should concentrate, given the fact that we have a very well-defined Q0 transferred by the cavity, we should concentrate on these 4 hotspots on the Fermi surface. These are called hotspots because are the spots, the positions on the Fermi surface that couples most strongly via this interaction, where you expect the leading order effects to happen. And so you can do other combinations. You can go in the pairing channel, or the pairing type of ordering, which would correspond for electrons in superconductivity, or fermionic atoms, which is called superfluidity just. And this corresponds to this bilinear, CC, and to these leading hotspots across the Fermi surface in the standard Cooper channel minus KK. I'm assuming here spinless fermions for simplicity, which means for ultra-cold atoms like spin polarized cloud. And there are still more competing instabilities. The other one is not the standard Cooper pairing, but it's the pair density wave, which means to take these 2 electrons here on the Fermi surface, and this is a gap function, which is now modulated in space with this characteristic momentum P0, which is not the Q0 of the cavity, but points in the orthogonal direction. This is a possible instability. And yet another one, which is the other couple of hotspots, but now not with 2 electrons, but with an electron and a hole, which is the formation of an exciton and the corresponding condensation, which is also possible and corresponds to this other bilinear here. So we have all these possible so-called channels that can compete, or ordering phenomena can compete. And my first observation is the following. You see that the corresponding order parameters for the standard charge density wave that I started from, we have a sum over the whole Fermi surface, sum over K. For the other ones, we don't have this sum, but actually every pair of hotspots on the Fermi surface work differently. I have one order parameter for every K, for every pair of hotspots. This situation where we have one instability or one ordering that comes over all the Fermi surfaces and the others have decoupled pairs of hotspots comes from the fact that we have an infinite range interaction with a finite Q being involved, very sharp structure in momentum space. And the fact that it is this charge density wave that has this sum over the Fermi surface, which can be called collective enhancement, comes from the fact that, as I told you, the interaction is naturally written in the density channel. It's exactly an interaction between these 2, if you want, order parameters. This is why this is the collectively enhanced channels and the other are non-enhanced. Which means that if I go on the attractive side of the coupling, where I have the possibility of charge density wave, if I write the phase diagrams using T over TF and G over EF, I actually have the Superadian transition at a coupling which is reduced by a factor 1 over n, like is collectively enhanced. To repeat again what I mean more concretely. Therefore, to look for these other 3 instabilities, I should rather go on the other repulsive side. And do they exist also there? And they do. And actually, if you consider them, consider only these 4 hotspots, or only the 4 hotspots, then they are actually all 3 degenerate. Exciton condensation, pair density wave, and Cooper pairing, using these 4 hotspots, are completely degenerate, meaning that they have the same TC. If I go beyond the hotspots at finite T, I find that the Cooper instability and the pair density wave instability, they are still degenerate. The coupling strength that goes linearly, it starts linearly with like a delta TC, which starts linearly as a function of the coupling strength, and plus polynomial correction, it comes from finite T. And the interesting thing is that they these instabilities, they exist independent of the sign of the coupling. You see on both sides of this axis, we have these transition lines of the pairing. And this is due to the fact that, again, we have an infinite range interaction which doesn't have the Q equals 0 component, it has the Q naught. This means that to come back from the Fermi surface, I have to go to, if you want, to second order in perturbation theory, and the thing becomes, you have equations that go like t squared equal to something like g squared, and then we take the square root, you take the modulus, and in the end you get a sign-independent type of transition line. And the second observation is that the exciton condensation, which is not in the pairing channel but in the particle hole like type of stability, it has always a lower TC. And this is because it involves particle and not particle and particle, and you need a finite thermal equation to have this dominate, and it has only just an exponentially small enhancement, and therefore it will always lie below these pairing instabilities. So in the end, the phase diagram looks something like that. On the attractive side, you have this charge density wave of super radiance. In a very small region, you might even have pairing, but if you go on the repulsive side, the pairing should be essentially the only thing you have. And so let's look at how the pairing actually looks like. What is how does this gap function actually look like on the Fermi surface? And that's how it looks like. I'm showing here the gap function in 2 dimensions on the Fermi surface and around it at 2 different temperatures, like corresponding to this cut here. One very close to just below TC, and the other here at T equals 0. And the first thing I want to observe is that here we have the gap function that has, first thing is that it changes sign across the center of the Fermi surface, so it has a node. Corresponds, you want, to B-wave type of pairing, and this is because we're taking spin-polarized fermions, so this spatial part has to be antisymmetric, and the fact that it's still possible on the repulsive side for spin-polarized fermions is because we have this infinite range interaction. And it has yet another sign change, which is in this direction, because it goes from blue to red also in this direction. And this is because the interaction is repulsive. So to have a finite gap, it has to alternate sign if you move by Q naught in Q space. Final observation, which I think is important, because if I didn't tell you whether this gap is actually Cooper pair or pair density wave, and it actually turns out that only at these 4 hotspots, only at these 4 points into the Cooper pair and pair density wave are degenerate. So they will, the fermions at these hotspots will not know whether, let's say, to order in the Cooper or in the pair density wave channel. But if you move away from these hotspots anywhere else on the Fermi surface, like here, this will be Cooper pair wave. So the take-home message is that if you want really a finite, like a relevant part of the electrons or fermions pair in this more exotic pair density wave, you need to be essentially in mu-1D. But then the strength of the cavity-mediated interaction makes this at temperature scales accessible. I can tell you more about the parameters if you're interested, but that's basically the main message. So I think I would like now to move to the second part of the talk, to the dynamical part, but I stop again for questions, maybe on if I completely said something unclear or something
yes,
like that.
Can I ask then a question? So you are ignoring any dissipation from the cavity, but I mean there is always a kappa. So how easy is to access these phases?
Yeah. So I will come to kappa now when I do the dynamical part, because it's very important there. For the static part, if you do this type of, if you write the interaction in this static approximation like here, so basically I go back to here where I have this term. Now, if kappa adds, then you will have a delta C in the numerator and delta C squared plus kappa squared in the numerator.
Yes, but there is another term. But
if you're far away,
but there is another jump operator that is proportional to the same term.
Yes. Mm-hmm. But I would say that if the detuning is sufficiently larger than kappa, the static part works in this way, and then you might worry about the dynamic part, which is affected by kappa in a way that I plan to tell you in the next slide.
Okay, but just
so I will see.
But if you have to do adiabatic preparation that is slow, doesn't hurt you at some point, because in order to reach the ground state?
well, that's a point that, there are, the answer to that question is, if I have a single cavity mode, you're right, the kappa will, the dissipation from the cavity will allow you to redistribute the atoms and actually bring them at long times to a temperature which is of the order of kappa, which is much larger than the ultra-cold temperature that they have. Same for bosons, but the time it takes for this cavity heating or cavity cooling to happen, it's long enough that this is not seen in the experiments with fermions I mentioned in the beginning. So is that your question?
Okay, thank you.
But then kappa affects also the interaction. Even if you don't analyze what kappa does on the distribution of the atoms in terms of being not thermal anymore or heated up, still it affects the dynamical part of the interaction. I want to.
Great.
So does it answer the question or?
Yes, perfect. Thank you.
Sorry.
There's
More
one more
questions?
questions here on the back.
Screen.
Can you hear me?
Yes.
What is the ratio between Q naught and K Fermi in your system, or like, is that also a parameter that you can vary?
You mean KF?
Yeah.
Yes. This can be varied in several ways, but I can say that, for instance, in this experiment here, where they have the charge density wave, I remember the value here is like, can be, depending on the type of angle of driving you use, I remember it's something like 0.6 kF.
No, sure, but for what you're presenting, is it at a fixed Q naught, or as you vary Q? Huh?
I mean, I can vary it, but it doesn't change as long as Q naught is finite. And it changes when Q naught becomes so large that you don't have any more of these 4 hotspots.
Okay.
When Q naught becomes larger than 2 kF,
Yeah.
then you don't have any more of this 4 hotspot physics, right?
Yeah.
And that makes sense?
Uh-huh.
Like if this Q naught becomes too large, then I don't encounter these hotspots anymore.
Right. But what I'm surprised by is that it doesn't change the competition between PDWs and Cooper pairs. But maybe that's clear? I don't know.
I think it will change this. It will change it in the 2 limits. One limit, as I said, when Q naught exceeds 2 kF.
Yeah.
And it will also change it when Q naught becomes so small that you cannot basically resolve these separated 4 hotspots. Let's say if Q naught becomes smaller in energy terms than the quasi-particle density or something like that, then you cannot talk about separated hotspots anymore. And then with a hot Fermi surface, this regime, then I don't know the answer yet.
I see. Thank you.
But otherwise, it's really, if I have a fixed Q naught, you can really exactly solve in mean field because it's complete forward scattering, if you want, in the language of solid state, but with a finite Q naught. I can demonstrate that there's nothing beyond mean field in the static part, and then I can really see that they are all degenerate and have this type of scaling of TC. Because it's in the paper we're writing, but the Cooper pair and pair density wave, due to this peculiar structure of interaction, can be mapped into each other if you have only the 4 hotspots, or only multiples of hotspots. And to complete the answer is the Cooper wins everywhere on the Fermi surface apart from the hotspots, right? The Cooper wins everywhere apart from these 4 points where it is the general pair density wave.
Okay, thank you.
Okay, I shall go to the dynamical part.
Go
I
ahead.
guess I have something like 15 minutes.
Yes, you are in 25, yes, at the moment.
Yeah. Yes, with some questions. So, the dynamical component. So, I go back to I have the same model, standing wave, single cavity mode with a given Q naught, but now I introduce back my photon. And I ask, what's the role of going beyond this static approximation that there was questions about? And to do that, to have an approach that includes, if you want, everything, we use, we write an equation not anymore for the Hamiltonian with a limited cavity, but we study the full scattering between two fermions coming in, two fermions coming out. This is called the Salpeter equation for the vertex function, and this sums an infinite series of scattering process and the quantum mechanical amplitudes, and it boils down to solving an integral equation for this vertex function gamma. When gamma diverges, it means that you have an instability towards the corresponding ordered phase. For those of you that are familiar with solid state, this is equivalent, at least for computing critical temperature, to the usual Eliashman approach to superconductivity, where historically one used this to study the dynamical component of the phonon-mediated interaction between electrons, which is indeed the relevant thing in standard superconductivity. So this is somewhat the equivalent approach, and I will start by making contact with the static approximation that I just finished discussing. And I do it in a simpler limit now when Q0 is much smaller than K. And I will consider only the Cooper pairing that we saw before that at least looked like the dominant instability. And the static interaction, as I told you, is like adiabatic photons or virtual photons, meaning that the characteristic energy of an electron excited by the photon is EF times Q0, and this is much smaller than delta C. And in this regime, there is a very well-defined static part of the interaction, and if I complete the static interaction in terms of this equation for the vertex function, I get this equation where gamma is the vertex function of two electrons wanting to pair being at the Fermi surface. And this equation, you recognize the factors that I used before, and this is the equation that I get from the critical temperature 1 minus 2 g squared over delta C Tc, and g squared over delta C was our GF from the slides before. And apart from a factor of 2 that I have to apologize about, which is a different notation between the two parts, I'm sorry, but apart from that, it's the same critical temperature we saw for the Cooper pairing at leading order in the static approximation. So let's say the static approximation means only considering scattering processes where the electrons or the fermions, by exchanging a photon, stay in the vicinity of the fermions. But always, there is another component, dynamical component, where these electrons exchange a photon, but not a virtual photon, but a real photon. A photon excited at its own characteristic frequency or energy delta C, which is the energy of this cavity mode. And this, of course, if delta C is much larger than VFQ0, brings the electron or the fermion far away from the Fermi surface on this shell. And in order for it, let's say, to pair, to give rise to this instability of the Fermi surface, it has to be scattered back by a second photon back to the Fermi surface. If I introduce these extra processes in this equation for the vertex function, I get this additional term. This additional term is proportional to the density of photon, which it makes sense because I'm considering absorption and emission of real photons now, not anymore virtual photons. It has this scaling again with g squared over delta C squared, which is our small dimensionless covering constant. And it has one thing which I find very interesting coming from a field where you want to mix quantum optics with condensed matter physics, which is you have a cooperativity appear here. People from working with cavities are very familiar with this. And this cooperativity is the cooperativity that involves, again, the cooperativity always has the coupling square in the numerator, and in the denominator you have the dissipative processes that work against this type of scattering process. And on the one hand, you have the lifetime of the inverse lifetime of the photon, so the width of the cavity that Anna-Marie asked about, and then also the width of the electrons, so the inverse quasi-particle lifetime of the electrons. And now, if you want, you can think about this being processes that scatter back and forth from the Fermi surface, a kind of two-level atom for every k on the Fermi surface. But in order for these scattering processes, which involve real photons, to be relevant, you have to have a high cooperativity of these transitions. And this means that the ratio of d squared over the dissipative process, meaning the width of both levels, being one, the Fermi surface determined by the quasi-particle lifetime, and the other level, or what we call the photon lifetime, is like kappa. So let's say you have a cooperativity appearing in an equation for a pairing instability because that the cavity has a resonance, and scattering processes between electrons or fermions can happen by exchanging real photons. If I consider now the effect of this on TC, I can solve this, and in this plot, I can find TC using, for instance, the Fermi liquid lifetime of electrons at finite temperatures here. And I find that compared to the BCS prediction, so the static approximation, if I have a finite number of photons, I can increase TC by putting more photons into the cavity by a lot, by even order of magnitude, by here, I guess, this value corresponds to I guess, 3.2 photons, I'm not sure, but the point is that the TC, as a function of the pump, if you, let's say, imagine pumping incoherent photons into the cavity, as a function of the pump strength, the TC grows linearly. So it seems that you can really inject photons to mediate stronger interactions, which is clear from this, but using here, I guess we used a realistic parameter for a solid, not for ultra-cold atoms, but for ultra-cold atoms, this formula will work in the same way, just you have a different lifetime, because it will not be, well, depending on whether they are interacting or not, but in general, the lifetime is different between electrons and ultra-cold atoms. But the message is, these resonant processes make you, allow you to increase the critical temperatures by a lot by injecting more photons. So this is the first, or the second, if you want, peculiarity of the cavity-mediated interaction, that due to the fact that the cavity has a well-defined energy, the photon in the cavity has a well-defined energy and momentum, and can be injected controlledly, you can make this dynamical component in terms of resonant processes very, very important, and use it to enhance collective phenomena. And I guess in the final 5 minutes, do I have 5 minutes?
Yes, kind of 3, and then 5 for questions.
Yes. So now we've seen, one last comment on this resonant process. We've seen that these processes involving absorption and emission of real photons, these resonant processes, they depend on the number of photons. So in general, they depend on the quantum state of the photon, quantum state of the light in the cavity. So one can ask the question, what happens if instead of putting incoherent photons or thermal photons, I put really more non-classical states of light? And well, you need to further generalize this vertex equation to being able to include this feature, but the first message I want to give is that if you do this, as soon as you have a non-Gaussian state of the mediator, not a thermal state, not an incoherent state, but if you have a really a non-Gaussian state, you have an additional structure emerging for this equation for the vertex that reflects the Hilbert space of the mediator, in this case the photons, and in this case the Hilbert space is the Fock space, most naturally. This is the equation for photon put in a pure Fock state. And this emergent structure can be solved iteratively in a way that I can tell you about if you're interested, but let me jump to the result, is the fact that not only by playing around with the quantum state of photons between like a thermal and a Fock state, you can change TC by a lot, but you can even change the most difficult thing to change, which is the critical exponent, the susceptibility of exponent of the superconducting or superfluid transition generated by this pairing instability. For a thermal photon state or vacuum state, you have a susceptibility exponent, which is the BCS exponent gamma equal 1. But if you have a pure Fock state, let's say, with more than one photon, let's say 2, you get gamma equal 3. And in general, you can show that the exponent is equal to a 0 number of photons in the Fock state plus 1. If you take a Fock state and you say in the experiment you can never inject the Fock state, you don't have pure Fock state sources, but you have very good Fock state sources. So let's broaden it a bit with a factor kappa. And you see that if you have a appreciable broadening, but not very large, it corresponds actually in this case to kappa large. So kappa in my case is the inverse of the broadening now. So sorry for the mess in the notation, but this kappa is not the broadening, the inverse broadening of the cavity line width, but is like the broadening in terms of Hilbert space, the inverse broadening in Hilbert space. But the message is that you can have few decades where the critical exponent of pure Fock states, and if you get arbitrarily close to the transition point, then you see that you don't have a perfect Fock state, and you switch back to the gamma 1 BCS exponent. So with this, I think I want to flash the summary slide, and thank you for your attention, and I hope there are more questions. Thanks a lot.
Thank you. So we are open for questions. In the back, yeah.
If you take your resonance to 0, like if you're like in the last equations, can you like arbitrarily increase TC in your
You mean
Delta
the
C.
cavity bandwidth here?
Yeah. No, delta C. Delta C.
The detuning.
The detuning.
No, because all my calculations work in this kind of perturbative regime where G square is much smaller than delta C square. Like this is a small parameter.
Uh-huh.
And this is, are you familiar, if you're a equation for phonons,
Yeah.
this is also called weak coupling there.
Yeah.
Because if you go in strong coupling, where the coupling between phonons and electrons becomes comparable to the characteristic phonon energies, then you go in this strong coupling regime where things change completely. And you have to solve this stuff numerically, these integral equations numerically. And I don't have an analytic answer there.
Uh-huh. Okay.
Right. More questions?
Thanks for a nice talk. Just wanted to ask, in the first part, in the static part, the results you showed were for electrons or for fermionic atoms, or for both?
I would stay for both if with a bit of optimism. Let's say the reason is the following. Let me go to the slides. In terms of model, so the first difference is that electrons normally don't couple to the density, right? The photons don't couple to the electron density, but to the electron
That's why
current.
I would sort of...
To make this model where I couple fermion density to photons, to make it solid, I need to use laser dressing. But this is in principle possible. People put serious numbers and you can do it. So in principle, this model is valid for both. This is why I call it light matter and not atom photon. What is very unnatural, however, in solids, is that we have a Q0, which is an appreciable fraction of kF. Because the wavelength of optical cavity cannot resolve the lattice spacing in a solid. And therefore Q0 will be much larger than kF in a solid.
As you said,
Which means that some interesting competition might happen, but you will not have these very well separated hotspots. So I cannot give you, so the answer about competition will be still interesting, I think, but not that simple.
but so you say that it's for both. I'm wondering then, I mean, how does this phase transition to, would see, if this, you predict it also for electrons, there are, all of these no-go theorems which they prevent from having this phase transition for electrons because of the diamagnetic interaction, the A square term. So
Yes, but these no-go theorems apply not to this coupling that I'm using. The no-go theorems apply to this coupling, to the
yes,
current.
exactly. But this is the typical
And
one for electrons.
I know these no-go theorems, they apply if you consider electrons current coupled to the photons, because this is the gauge theory then, and the magnetic coupling you need to maintain gauge invariance, and if you violate gauge invariance you get a transition, if you restore it you don't get it. But it turns out that the charge density wave transition, what I call charge density wave transition, if you look at it for these models, where you couple to the current, those are states where you have a finite current of electrons and a finite number of photons. And there is no coherence for the Q equals 0 version of it, but there are now several papers showing that it is possible for finite Q there too. So the no-go theorem doesn't hold, even in solids, to look at finite Q superradians.
Okay, thanks.
Okay.
Maybe, related to the question that Vasilis just asked, can you say a bit more about the realistic parameters in experiments? So at some point you said that D has to be 60% of the Fermi energy. Is that realistic in experiments? And then further later on you even said that G has to be smaller than delta. So how does this are there experimental platforms that realize this parameter?
Yeah. So if you talk about the first part, about the static competition, we took exactly the parameters that are valid for ultra-cold atomic experiments. with them. So we took really the numbers from the experiments in a BFL that I cited in the beginning. So there they have a cavity at an angle with the trapping of the cloud, such that the Q naught is 0.6 kF. So it's really perfectly in this regime. The delta C is like something like at least 10 or 100 megahertz. Kappa is several kilohertz. So it's really in the regime we consider. And then the G can be tuned and is never as large as delta C, but it's appreciable such that you can reach, let's say, this pairing. And the relevant question that you might be in the end asking is, let's go on the repulsive side where I don't have to fight with the charge entry wave, which has been already seen. And what is the T, the pairing on this side, given the maximal GF the experiment can reach? And for that, we put the numbers, and you are very well, with reasonable effective couplings that you can reach in this experiment at the PFL, you find that TC for the pairing, which is of the order, can be like 0.1 TF or 0.5 TF, which is the temperature they already have now.
Thanks.
So that answer, this answer is for tackle atoms. For solids, I can give you a quantitative answer, not quantitative for solids, but I can give you a calculation we did for realistic parameter for solids, but this we did only for the Q equals 0 case where we didn't solve the competition, but we just looked at pairing, and this is what I showed you in the last part, where I showed you this increase in TC. But for root code atoms, we really have no fitting parameters, so I'm more confident in putting numbers.
Thanks.
Great. A very, very short question. So, but for the adiabatic elimination, you need G square root of n. Yes, it's not only G. Delta C has to be is G square root of n. No, because of the collective behavior for the adiabatic elimination.
For the adiabatic, you mean for this part, for this to be valid? Well,
in general, when you adiabatically eliminate the photons, you have to have G square root of n.
You square root of n, you mean the square root of atomic,
yes.
of atoms?
Yes. Because it's collective, so you have to have this term smaller than the energy of creating and absorbing a photon. But okay, we can.
Might be, I need to review my calculation, but I can believe what you say, yes. Yes. But you know, it's still the experiment is easy to enlarge delta C.
Yes.
It's difficult to make it below kappa. Yeah.
Yes. Okay, great. Okay, I think we are out of time. Thank you very much for the very and we are at 8:50. Great.
That's fine.
Stefan?
Yeah.
Could you keep them for 1 second?
Yeah, sure. Wait a second.
Okay.
Hey, Francesco, thank you so much. Wait a minute.
Hi.
Hi. Yeah, you can come here maybe and use this video.
Is this strange? I mean, this is pretty weird here. Hi.
Wait a minute.
I see you guys.
You can see us. Okay, so yeah.
The one question I was wondering is, this cavity, laser-driven cavity stuff is very cool. Do you guys have an understanding of how to renormalize the Coulomb interaction? Is it a standard situation where the detuning you should like integrate the Coulomb down to the detuning? Or because I mean you guys.
Pretty well in the Zoom.
Yes.
That's okay. We
You have subtractive interaction right down in the
Yes, I would like to.
So there's a Coulomb interaction that is present in all solids, right? So is the right way to, like, if you do adiabatic elimination naively, you just focus on the dynamical term, this is, you said, just like the one-on-one couples.
I don't need to.
And even in that problem, there's no Coulomb force that you have to fight. So typically, you like integrate down to the level of the omega divide. Yeah.
Yeah, well, in a nutshell, my answer is we do exactly the same.
Okay, I see. The question. Oh, okay,
We do exactly the same formally with this we actually don't do the advanced elimination. To turn the manuals that I do, like the final process I showed you, they are exactly not doing that. They are using really the full dynamics.
Yes, for me, it was long time ago when I was here. So bad, but time flies.
No, that's fine. But you have a Coulomb interaction.
I wish, but
Like,
time
electrons
flies.
repel each other electrostatically. How do you like combat? Like typically there's a competition, right, between like
But it's
lambda and
as nice as it was.
mu star.
Oh, really?
Yes, congratulations for your
Thank you, thank you.
Like in the Macmillan formula, right, there's a Coulomb pseudopotential there.
Yeah, no, it's a
How do
very
you
nice
think about
place.
this? Have you
So
guys
how
thought
long
about
have you been?
Well, we didn't put it seriously in the calculation apart from putting it as a life.
And you're also working
We did
on...
especially with people like
Oh, okay.
we can, it would be easy to do it like in the beginning, a small business.
That's
I have been seeing that you have a lot of
I would
work.
say that
Yes, we are also excited in campus. Yes, James Thompson is there, so it's very interesting. Yeah, we are trying to look at pairing, but artificial pairing. Artificial, using the Spin-Anderson model. So we don't have, we have Fermi, but we don't use the statistical It's Fermi, but we can, this is artificial, but we can exactly emulate the Anderson-Sebesky matrix, so we can write exactly the BCS Hamilton, where you have the Cooper pairs, the Anderson-Sebesky, the Cooper pairs are spin up, empty cycles spin down, and this is everything of the Richter space at low temperature. So this is exactly what we can engineer, and we can see all the dynamical. The theory is out, but the experiment is just to be out, where we see the theory.
Is the paper I can find it or the theory paper?
It was already
But I am
2 years ago,
concerned about
but took a little bit to the experiment to catch up, but as usual.
It's always the case.
But finally, there's all three phases, all the dynamical phases for
these calculations.
yes.
Here,
It's
there's-
cheating.
this is only from attraction,
We don't have
right? So
to
it's the
do
same as like the
any
BCS
low
TC that you
pooling
can write
because,
down.
or
And
do
like,
optically pump.
that you do in class,
That is
for
much
example.
easier to reach
Right?
for temperature.
But
Yes, so
but it doesn't have mu star,
Cooper pairs
which
have
is
less
like
spin
how,
degree of freedom.
you know,
So for
by that
seeing
logic, every
the
fermionic
the
system,
phases
every metal that you have, because there are some bosons around,
and we don't have to do that. We just have to optically pump.
there's some competition
So-
between the bosonic medium interaction
Yes,
and
yes,
Coulomb
yes,
repulsion.
sounds good, sounds good. Yes,
Where does
yes.
that come from? Or how do you think about that?
It's not.
Because I've been looking at this mostly from the electronic side.
I see.
What do you like these phases by the cavity to the electrons?
Okay,
But,
okay.
I'm not sure my question is
Fermionic
coming.
atomic
I understand
Yes.
this is fine
Yes.
if you,
This is
there's a
because
repulsive
they're also
interaction
driven, or
just because of
it's a driven
electrostatics.
cavity.
Not
Forget
necessarily.
cavities
No,
or drying or
we
anything.
don't
Any
dry.
material.
It's in vacuum
You have an
because it's an
electrostatic
electronic
repulsion of
transition. But it's
Right? It's screen Coulomb potential.
of course you need to
And you
apply
have to keep,
pulses,
like, you have to
otherwise the atoms are in the
compensate
ground state.
the attraction.
But
I
as
think
you
maybe
drive them,
that's
that's
the
it.
response to it.
You generate, you drive them, stop driving.
What is the title of the paper? Do you remember?
I might follow up, but like,
quantum simulation of
you understand what I'm
BCS.
saying?
In my talk, I will have a small talk, but it's quantum simulation. I mean, I'm not going to talk about that, unfortunately, because of the time, but it's quantum simulation of BCS model
So
in
not all
an
materials are going on
Yeah,
the
these days it's around, it's not.
It's a game of not all materials are going on mediators. You can't just pull down any material and just get it. There's some balance between like the cool propulsion and attraction. Right? So where is that reflected in your formula? Or have you guys?
I guess so, exactly.
Well, we didn't, so this competition, we didn't put it to compute this number. Because the point of this calculation was to show you can increase the C by putting more phonons into the cavity, which you cannot do putting more phonons into the cavity, because the phonons is difficult to, they don't have a shunt or energy structure. They have not a well-defined resonance. They can transfer all momentum, and therefore these resonance processes can get close to the Fermi surface. They cannot pick up, they can stay resonant, and therefore the increase of the C, or if you want this cooperativity, is small because this kappa process. And so that was the concept. And that's the point we make, and this is really by putting more photons now, you can obviously can win the competition.
I agree.
I'm not saying that you can win every material.
I agree. That is, I think, very promising. Because, like, if you but this is
Go across
that I think is very interesting.
constraints.
Yeah, so you have real phonons.
Right. I can give you 10 Kelvin or 1 Kelvin.
I mean, you can give me 1,000 Kelvin during this, right?
Transition happens.
Because you can just
Why?
swap
Because
the number of
if
photons in your
if you're
cavity,
below the threshold,
right? And then your CC will be like 1,000,000.
very fluctuations
Oh,
of
what?
the density of the force compensator is not completely
I
flat.
think that surely happens is that in the linear theory,
So
even for
why
phonons,
if
there
you
is
have a
the
laser
diagonal
because the glass is
You mean
fluctuation of the density, you get a little bit of scattering, even though it's not coherent, it's not constructed.
this is not as bad
I
as
was saying in normal phase, there's no scattering at all, just to make it simple. So not time you get photons scattered, it's very easy for these photons to escape through the mirrors. Then nothing much can be done. But at a certain point, then all of a sudden the field can build up.
I think I'm getting
And then you have two
I'm
sorry. And you have two standing waves.
Thanks for giving the talk, yeah, let's catch up soon.
To produce a two-dimensional light field, which is two interfering standing waves. And this gives you this chicken. This lattice, once it's supports according distribution of density of the atoms to light waves. Like in an optical lattice. So the atoms order this light field. And the ordering of the atoms again support to keep up the light field, because otherwise you don't scatter photons. So it's kind of both sides to create this new situation. No, particularly strength. Frequency of the guiding field is
No.
Getting there.
It also plays
How
a
much
role.
time does it take?
Oh, we still have.
Couple of detuning.
So I have 35 minutes
Very
to make
large.
that question.
Yes, exactly.
And you give me after 30 minutes
As a
transition
transition.
and the frequency. This is many nanometers. So for that to make a change, you have to really move the detuning a lot. You're not talking about a couple of megahertz or something like that. Terahertz, many nanometers.
linearity of the PC makes the cavity essentially
It starts with fluctuation of the density of the Bose-Einstein and scatter a few photons into the cavity. But enough photons so at the same time you're not losing all the photons again as the mirrors. And once you go above that threshold, then you get the finite density, finite standing wave.
Das funktioniert leider nicht bei mir. Keine Ahnung, kommt schon. Bei dir hat es funktioniert.
So then you get a standing wave that has sizable depth, and the atoms are get trapped at the intensity maximum because we're ready to which is the case only
you associate this with the essentially when you go to the thermodynamic limit between the two levels. So it's not really the same.
No, it's not quite the same because we have
the community.
right. We are in an open and that makes it a little bit driven. So I think it's the same transition. Only that the openness of the system adds a little bit but I think it's still okay to say this is a very alternative transition. So where are you? I should work.
Before I did actually my PhD.
Did you? Oh, with the Rubio. When was that?
I graduated in 2021.
I see.
7 years I did my master's in PhD.
So we should have crossed.
Yeah, many times because our buildings were like 100 meters apart.
And that's when I also asked because you are saying you are very far from you are very far the moon.
Yes.
So that means that we for the
No, the dissipation has
Geh noch kurz runter und schauen wir dann. Na, das machen wir auch.
atomic sector of the system and matter sector. There's no dissipation directly connected to the atoms. There's no
yeah, okay, but I think the variance and I mean you have elastic interaction and that is just
dissipation. The dissipation is only via the photons.
yes, kappa. That is what you are in when delta, the is much larger.
The detuning is much larger.
Exactly.
Extremely much larger.
Exactly. So that's the part that I understand. Then, because in many cases, then you don't have to kappa disappears from the problem because it's much larger. Is the pressure the time scale at which kappa kicks in is much longer.
Yes.
So that's my question. So when they start to see the what is actually the loss of the driven by the elastic
Okay, so you were talking about months ago, Looney Tunes scheme where we have time. The first time, the discrete time is what I was talking about.
The initial time, yes. When you, or the continuous time, you were talking about the continuous time. My understanding, you were saying dissipation is an
No, I think the dissipation is important.
It is important.
Yeah,
Exactly. That's the part that I
but the tuning is not really important. The tuning is just large enough to make the intervention between light to be simply as if you have an index of refraction. That's so. And if you change the tuning a little bit, nothing much changes. Well, but there's the this is it's not easier to explain to get a intuitive picture of that. The main point I think is that you have the atomic sector that can adjust to a change in the photon sector at a time scale given by the recall frequency. So you have to schedule photons that requires a recall time, one over the recall. That's the time scale for that. And then you have other time scale so photons to adjust for a given setting of the matter. This is coupled.
All right, so So we are back for the second part of our morning session. Okay, perfect. Hello? Yes, great. So we are back for our second part of the session today in the morning. So our next speaker is Susan Jelin from Harvard University, and she's going to tell us about superradiance in arrays, new insights and applications.
Good morning to everybody, and my apologies, I'm totally flustered because the technology doesn't work. There are interesting problems that you have. My problem is actually purely mechanical. Namely, the two plugs don't fit next to each other into the computer. So be careful when you buy a computer. All right, so I will just stand here and advance this this So yeah.
You don't need a microphone either, so.
So it's fine. Should I switch it off? Do we need it for Zoom? Or?
Yeah, we need it not for Zoom, for the YouTube. It's okay.
Okay, so I will take this a little bit further down and not speak that loud. Thank you, Hossein. Okay, let's get ahead. So, superradiance was found 70 years ago by Dicke. And then 30 years later, Gross and Laroche wrote a review that basically everybody learns from. There have been some advances, both in superradiance and in general applications. And so these days we just ask ChatGPT, and I'm not going to read that for you, but it's actually a pretty good answer. Okay, so let me just very briefly, I know everybody has talked about that, but I would like to give this very brief introduction into superradiance. So if we have a single atom that decays, we get an exponential fall off of the intensity over time. If we do that with two atoms that are far apart, we get the same thing. But if we put the two atoms close together, we see a little bit of a change in this time signature. This is, by the way, the intensity per atom. And then, of course, we can do a lot. like for example 10 here, and what we see here, and what I actually do need is a laser pointer. So what we do see is this initial flash of light that comes out in the superradiance. So this is somehow the kind of smoking gun for superradiance. What kind of one knows about that is that this is an effect that goes with n squared, and it's due to constructive interference because we are actually adding up all of this kind of light amplitudes here. And there is this so-called build-up of collective dipoles, which is actually a little bit of a misnomer, but I will not go into this, other than this one here. So the basic background for all of these cooperative effects are dipole-dipole interactions, and these dipole-dipole interactions are really, and Tilman Farr was telling that yesterday already, we do not have any dipole moment for any of the states, but we have this exchange interaction of excitation of two atoms. So we have one atom in a ground state, one atom in an excited state, and we have this exchange where they exchange the excitation. And this leads to the dipole-dipole interaction. That's basically what the whole talk is about. Let's introduce Dicke states. Dicke states are the fully symmetric state of n excitations in large n particle. Here I have the second excitation for 4-particle state, and as you can see, this is the fully symmetric states. And these are the kind of states that decay with this n squared speed up. And the best way to describe that, if you want to really fully describe it to every detail, is to go into an angular momentum form, and then this looks like that. And the leftmost column is the n half angular momentum state, and these decays are the Dicke decays are these yellow arrows. And if you want to do Dicke superradiance, this is all you need, and you can throw all the rest out, and in principle I could go home. However, if you add dipole-dipole interaction, that dipole-dipole interaction is typically much, much smaller than the energy difference between the states. And that connects all of the other lower symmetry kind of manifolds to the system as well. And the whole problem becomes a 2 to the n dimensional problem, and that is usually very hard to solve. What one sees very nicely in this picture is also that there are a lot of lowest state in each of those manifolds, which kind of cannot decay fast anymore because they are at the bottom of their manifold, and can basically, if you are here or here or here, you can get out of that only via dipole-dipole interaction. And so this is a slow evolution, and this is what we know as subradiant states. And in principle, this is all the physics, right? I mean, if you fully understand that, we are done here. Let me nevertheless tell you somehow a little bit more. So I show you some ways how to calculate this. I will kind of go into the question of the collective length shift, tell a little bit about subradiance, even though this kind of got crowded out, a little bit about entanglement and applications. And in particular, the calculation is, of course, if we have realistic dipole-dipole interaction. And in particular, about the collective lamp shift, the main question is first how to even define it. And then, of course, how to calculate it. So I will start, however, so I gave the title of this talk as superradiance in a race. I will not do everything in a race, but I will start in a race. So we are kind of thinking about kind of 2D ordered arrays of that type. And I have put a couple of references here because they should all show up, and I just decided I list them all here. So this is kind of the latest ones that we have here. Dicke superradiance is a phenomenon with the atoms that are in a they start totally inverted, and they are in a point-like sample, and they synchronize and emit light coherently, as you have seen before. And And recently, people have looked a lot what happens if the ensemble is actually not point-like. So, like for example, our 2D array. And there's of course a lot of this done, and a lot of the people who have done it are here. And I'm not going into any of these details, and this is also by no means a comprehensive list. I just give you a little bit of an idea of how we approach this. So we start with this system, and here in particular, what is important is these are two-level systems, and we have a lattice constant, or in general a distance between atoms that's smaller than the transition wavelengths. And we have here really the typical way of calculating this. We have a Hamiltonian which includes these coherent interactions via dipole-dipole, and a Lindblad operator which includes both the collective and the individual dissipation. And this interaction strengths, both the coherent part and the incoherent part, are the real and imaginary parts of the dipole-dipole Green's function. This is basically what is here in the picture. And what we solve is the total master equation. And this, of course, is a complicated long-range interaction dissipative many-body system. And all of you know that you always need to use some tricks to solve this. So first trick. We use cumulants. And this is actually, there is a nice package which was developed in Innsbruck, which you can download. Which does this automatically for you. It's actually very nice. So how does this cumulant expansion work? Here's basically this system again that we have before, and what we are doing is we are calculating expectation values, both first mean field and higher order correlations, and take the cumulants, which are basically the essence of correlations. And this program that I gave you before basically does this for you. So the equations, they look really pretty, and you don't want to do this by hands. And this is, I think, up to third order here, what you see on the right side. So it gets better if you go to higher order. Okay, so let me answer just one single question using this. There's a lot of questions that you can answer, and many people have done that from several aspects. So the question is, given lattice spacing, given atom number, given geometry, when do you get superradiance? So one way to look at this is to look at the time evolution. So I'm sorry, this is actually time, logarithmic time here in orders of the natural decay rate. And the lines that you see here are time traces for different sets of parameters here. It doesn't matter what they are. So some of them have a slope that goes downward to start with, and some of them have a slope that goes upwards. And this is actually a pretty good possible definition for superradiance. It's not the definition, but many people use this. And so what we actually need to look is to look at the total the complete decay rate at t equals 0, and if the slope of that is larger than 0, we call it superradiance, and otherwise we call it not superradiant. And that's, of course, with a nod to this kind of initial burst that I told you before. The second order correlation, a cumulant formulation that I just showed you before, governs obviously dynamics at early times, so that's a very useful tool for that. So again, let's assume we have a fully inverted system, then we can, in this cumulant approximation, write the solution for this problem analytically. And it's actually pretty simple, and it depends only on the gamma part and not on the shift or J part of the interaction. And of course, we are not the only ones who looked at superradiance. There's, for example, a paper by Stewart, who also looked at that both in 1D and 2D. But what our cumulant calculation can do is it can also not just tell you how is the slope here, but also how high does it go, which is obviously also a pretty good measure, right? And in particular, you see that it's very important. So this is only for 4 atoms here, either in a line or in a square. And this white line that you see here is basically the limit of that one would get from this pure kind of initial slope here. And you can see that this seems to, so here's the maximum of this maximum here. This is the color coding here. And what we have on the axis is the lattice spacing and the number of atoms. And you see that the really kind of interesting stuff happens actually pretty far away from this limit. In particular, if we look at how this strength of the superradiance scales with n, for 1D, that seems to follow pretty much the same kind of line shape that you just saw before. But if you go into the 2D lattice, and please do note this is here logarithmic, one actually sees that depending on the parameters, and here the parameter that we changed the lattice constant goes with the power law. And here we even can kind of plot this power law as a function of this A. And please do note that we go here into a couple of 100 atoms, which is still kind of relatively easy to calculate.
Are they both on log scale?
No, the first one is not. Because that one does just not give anything interesting on the log scale.
More and more atoms, it just reaches a plateau essentially, right?
Exactly.
While the other one, it goes some power low.
It goes with the power law, and as far up as we could go with the atom number, this power law persists. So the next question, which is very related, is how many atoms? So far this was fully inverted. So next question, how many atoms do you actually need to have excited in your system in order to get superradiance? So this is if you optimize all the other parameters, how many atoms do you need? And you can do that analytically as well. And you get this formula, which depends on the same parameters that we saw before. Please do note that what we are looking at is a system like that, where we say we either excite an atom or don't. We don't have any coherent oxidation or something like that. And this expression that we have here is an average over all possible kind of configurations that we get here. And if we compare that to the Dicke case, where we have these excitation point-likes, a point-like that basically simplifies to the fact that we need to excite one more than half of the atoms in order to see superradiance, which should not come as a surprise. Okay, so that was the kind of somewhat straightforward way to calculate this. Now I would like to, and I will get back to that, but I would like to kind of now introduce a way how to calculate really big, three-dimensional, homogeneous collections of two-level atoms. So this is really basically the opposite end of a limit case. And here, this kind of atom by atom kind of master equation approach doesn't work anymore. So what we have to do here, we have to do some averaging much earlier. So here is how this works. So we have our ensemble of atoms. We write an Hamiltonian with all degrees of freedom. And then we select randomly 2 probe atoms and define all the others as surrounding atoms, such that our full dynamics is now a description of 2 atoms plus a field. And that gives us an effective 2-atom description. So how does that look like in mass speak? We have obviously the atom and field Hamiltonian, and then we have the interaction Hamiltonian, which is in a typical dipole approximation. And then this selecting of 2 atoms and field means we define as the interaction Hamiltonian only the interaction of the 2 probe atoms with the field, but the field is now a dressed field, which is already dressed with the interaction with all of the other atoms. So it's really, it's the same, has the same amount of physics. So far, there's no approximation. This is all still exact. It's, of course, undoable, but it's exact. And then we can write that as an effective evolution operator, which we then can calculate with. Please do note, one of the main kind of obvious differences that treats the dipole-dipole interaction exactly the same way as what you have seen before, but it's never really spelled out explicitly. It's all basically hidden in here. It's basically if you take this expression, put it in a Green's function, and then integrate the Green's function out, but we don't integrate the Green's function out. So that's basically the idea. And so this this effective two-atom description comes, now we have to make a couple of approximations. So we also again go into a cumulant expansion and keep the cumulant expansion to the second order. So this is the main approximation that we make here. And then we trace out all the field degrees of freedom because we are interested in the dynamics of the atoms, and then we have a two-atom master equation. And that one gives us a lot of, we cannot solve that completely analytically, that's very nonlinear, but it gives us an analytical dependence on all of the necessary parameters, and therefore is super useful. Okay, so what we, for example, get from that is here, this is the excited state population, which here we actually haven't started with fully inverted, but nearly fully inverted. And this is again, please do note, this is again on a logarithmic time scale. So we have this really fast decay, which is super radiance. At the end, we have radiation trapping, but this plateau in the middle here is actually subradiance. And that was something. In the meantime, everybody knows this, but when we first found that, we were a little bit surprised. So here we go into a little bit more detail and do that for various optical depths. So here you see the optical depths in the color. And the time trace for the vacuum decay is in black here. And what you see is everywhere this super radiant decay, this long plateau, which gets longer as the optical depth goes up, and then this final decay, which is actually radiation trapping. So radiation trapping is a completely incoherent process, which consists just of reabsorption and re-emitting of photon, which is completely incoherent. So you don't need quantum for that or anything like that. Subradiance, however, is a very quantum effect. So obviously, there's something happening here somewhere in the middle in this subradiant. But in order to figure whether this is really subradiance, we had to prove that this is really coherent here. And so what we are plotting is here the two-atom coherence. Please do note that the single-atom coherence, which we usually write as rho EG, is zero everywhere in this case. But this is the two-atom coherence, and that actually does get non-zero exactly over this time frame when we see this subradiance. So it is subradiance. I think this is pretty clear. Here I have shown the intensity per atom. That's the same as this Gros-Haroche picture that you saw before. But here also scaled by the optical depths. And you see that this is really, this whole superradiance is really completely universal. Right. So that's actually something, and it's not very beautifully universal if you're still at small optical depths, but starting with a certain optical depth, somewhere between 1,000 and 10,000, it becomes universal. Okay, so this is what we can do. So let's look at one application of this, and what we are looking at is molecular laser cooling. So here are the two lowest electronic states of a molecule. And this, of course, has vibrational levels and it has rotational levels. And the question is, how can we laser cool this? We are not the first people who ask this question. We are definitely not the first people who came up with the knowledge that we need for laser cooling a cyclic transition, sorry. The cyclic transition, however, nearly don't exist in molecules. There are special ones, and you can use some tricks, but a priori they don't exist. So what we are planning to do is to use just the lowest vibrational transition, because the first excited vibrational state obviously has nowhere to decay than the lowest one, right? So it's certainly cyclic, but it's also super, super slow. So if you just let it sit there, and you can laser cool for a long, long time, right? So what do we do about this? Well, we use superradiance, obviously, otherwise I wouldn't talk about this here. So how does that go? From this, one could actually, from this treatment that I showed you before, read off that the decay rate, in particular in the very superradiant regime, pretty much goes up by the optical depths. This is a bold statement to make because the decay rate is not really a rate anymore as we know it because it's not an exponential decay, etc. But as a kind of a rough estimate, this one does actually pretty well. So what is the optical depth that we have? So optical depth is the number density times the wavelength squared times the size times the population of the upper state. And here I have put a couple of numbers in which could be kind of feasible for molecules. And what we see is that we get about a 10 to the 5 order of magnitude increase. So that should in principle work. But we should of course prove that this really works. There is another problem, namely the momentum kick of these large lambda photons, and the examples that I just gave was 100 micron, right? I mean, that doesn't give you a lot of momentum kick to cool. So what do we do about that? Well, we make a Raman transition. And the Raman transition is to the excited state, and therefore, if we make the beams counterpropagating, we basically get 2 optical photon kind of momentum kicks per decay. Okay, so then it doesn't look so bad anymore. So how does this work? Well, not a problem. We don't want any, because of the cyclic transition business, we don't want any excited state population because they typically decay wherever and are gone. So what in our case, the way we model this, we have a state 4 and whatever is in state 4 is in the black hole, never comes out anymore. So solution is use EIT. Okay, and EIT is well known for the fact that you drive between 2 lower states and the upper state never gets excited. Okay, and it turns out that actually works pretty well in this case. And here is some results of where we do this. This is the velocity of the molecules on the average in units of the recoil velocities. And for the example that we have here, and I forgot what mass we took, but what we get here is kind of in the nano-Kelvin regime. So this is crazy. It works very well. Why does it work so well? In principle, because of course the Doppler limit for a vibrational transition is tiny, right? This is of course not realistic. There will be some broadening which make that much bigger, and we have not kind of fully taken that into account here. This is basically just a best case scenario. One thing that I kind of also dropped a little bit under the table is that, of course, a real level scheme cannot have a closed 3-level transition. So we have to actually go to a 6-level transition, which means we have to look at 2 rotational states per level. And this is actually how our simulations have been done. And the final figure of merit is how many molecules do we actually keep. And this is the time basically for, as you can see, for a couple of different of these time traces before, but in particular the one where it's fastest. So the point is we would be about here by the time we are at the minimum of the cooling. So we lose half of the molecules, but in principle this I think still kind of it. Okay. Then I should actually say that was a project that I did with an undergrad who is kind of not an undergrad anymore, but Caleb did basically all the simulations here. Okay, so the next question is the question: what is the collective lamp shift? So the lamp shift, not collective, just lamp shift, is the result of the interaction with the vacuum fluctuations. I hope you've heard this. In the case of the altered density of states that we get inside an ensemble, the value of the shift can change. And in particular, if we have a very high density of radiators, that can be considerably altered. And what comes out is what we call the collective lamp shift. Okay? And in particular, I give the in particular in 2 slides. So this, of course, has been also done. There was 10 years ago, or more than 10 years ago, an experiment in the Adams group where they put a cell inside a very narrow pair of plates, and they change the thickness of that so that they can really do that as a function of propagation length. And this is how the cell looks like, and this is what they got. This is only the shift, or this is what would be the collective lamp shift. And in principle, it's a great measurement because it's really vacuum. They send a very weak probe field through the etc. The problem with this is that that they later found that a lot of these oscillations that they have here actually are internal kind of cavity reflection. So they basically did that again. This is this lower paper. But in that new paper, they don't have such a nice picture anymore. So they do it all a little bit more careful. So I don't have anything to compare here to. So how can we calculate this? Oh, and this is actually what you find in Gross-Roche. This is a classical calculation for this. But here, let me get a little bit back to this calculation that I introduced to before too. So the total collective shift, which is delta, has, and both the gamma and the delta, which is actually before I called it J and delta, the J and gamma, so now I call it delta and gamma, is actually just an integral over the Green's function. Please do note that these fields are these stressed fields that I mentioned before. And if you look a little bit closer, we have a part that is basically proportional to this commutator, which is basically this commutator between A and A dagger, and is therefore 1 and is therefore independent of the intensity. We could also have a stimulated part, which is also part of that, which depends on the number of photons, which if we have superradiance is totally overwhelming. But if we have basically a low light level, we see only the spontaneous part, and this is what we call the collective lamp shift. This one, I don't give you any more of the calculation because it's rather complicated, even though it's easier than the whole thing that we did before. These gamma and delta depend on all kind of pairs of atoms I and J, and are nonlinear functions of the vacuum decay rate themselves, the atomic state, the tuning at which we probe it, and the number density. And what we find here, this was actually Hans Schen's work, who is also sitting in the audience, and some of the stuff that I showed before as well. So we find, yeah, we actually do get quite some changes depending on the number density here, and that it also follows Kramer's conic relation, not very surprisingly, and that it becomes very unsymmetric the denser we get. And we can also see that, and here I should say, sorry, the first that we calculate is for I equals J, and this one can also be plotted as a function of the density of atoms. The second part is where we calculate the pairs where I is not equal J, and I will get back briefly to that afterwards. So please do note that falls off for distance very quickly, both of them, both the delta and the gamma. But is actually of a similar order of magnitude as the decay rate. So the problem is how to measure this, and this one actually kind of stumped us for quite a while. And then we figured what it is the best. We take some kind of given volume, for example, here just for simplicity, it's sphere. And calculate the single atom susceptibilities from all these gamma II and gamma IJs and delta II and delta IJs, and calculate the single atom susceptibility chi I then average the chi over the whole volume and define a gamma effective and a delta effective depending on this chi effective. And if we do this, then we find an effective, both an effective change in the spontaneous, or the broadening in this case, and the lamp shift that could actually be measured. And here you see the result, and you see actually a form that is reasonably similar to the form that I showed you before. To my knowledge, this is the first kind of general calculation of this kind of quantity. Okay, so now I need to, I need to cut off a little bit because I've only 3 minutes left or so, even by my clock, which is slower than Anna Maria's. Let me just. This is interesting. What I leave out is interesting, and Stefan, please forgive me. I'm happy to show this, where we show a little bit of how actually driven super radiance scales with atom number. Just to give you a little teaser, we get a result that seems to contradict the experimental result that was found by Brouwer, and we find also a way how to actually explain it better than what was done so far. But what we do here, and that's the last part, let's look at spin squeezing. So spin squeezing is also driven superradiance. So what we need for that is a many-body quantum system, some interaction, an external drive, and what we don't need, but what we have to deal with is dissipation. There's, of course, a lot of spin squeezing with superradiance which has been done, also again partially by people who are in the audience, and it's even being used for actual quantum metrology. So here, remember, I showed you this collective shift. So turns out that for spin squeezing, we need this parameter. And we need this parameter. So this is the lamp shift. This one is this kind of change in broadening. And we need only the spontaneous one. And what we do, just in order to show you these two pictures that I have left, we average this quantity here over all possible I not equal j kind of gammas. And we call this gamma bar. And it turns out that you actually do, even in the realistic dipole case, so I should actually show it, sorry, just go back briefly. What you see here in these old papers, both by Alejandro, Diego, and ours, is for Dicke state. In this case, we do it for a dipole, and we see indeed that one sees spin squeezing here. Here, this is for different optical depths. And here, this is for a strength of this gamma bar, which I just defined of 0.1. That seems relatively small, but we actually get reasonably strong spin squeezing in this case. Just as a test, we set just by hand. We leave everything else the same. We just by hand set this gamma bar. As small as it is, equal to 0, and all the spin squeezing vanishes. So this is, I think, very interesting because it tells you where the spin squeezing actually comes from. And with that, I will finish. That's my group, and these are in particular the people who did most of the work. So Victoria and Caleb are undergrads. Han Shen did all of these calculations with the averaging over large systems, and Oriol and Stefan did all the other calculations. And with that, I will thank you.
Perfect. So we are open for questions. Maybe
Thanks for the great talk, Susanne. I just want to ask about the collective lamp shift. So at least the one I know from textbooks, like when you have the hydrogen atom interacts with the vacuum, then you have 2s and 2p levels, but they split apart, right? Mm-hmm. Is it exactly the same thing you're computing or something different?
Thank you for that question. So yes, and what I'm showing here is actually, I already kind of renormalized the vacuum lamp shift away. I should have said this. So the gamma bar that I show is already minus the vacuum lamp shift. Because the vacuum lamp shift, of course, I mean this in particular, the singularity that you get there is still there. So what we have here is on top of this.
So
and because, yes, it's on top of that,
one.
and of course it's not S&P and whatever, because we are dealing with two-level atoms, okay?
That's also what I want to ask you. Which kind of atom are you having in mind, or which atom was done in, was used in the experiment?
The rubidium.
Okay.
I think it was one of these typical kind of rubidium. But the change that you see is really a change due to the density of the states, density of the atoms.
It's a collective enhancement.
Yes,
of
exactly. Yes, and thank you very much, because that's of course important.
Thank you. Great.
Great. One more question in the back.
Yeah, thanks. Just a quick question regarding the molecule cooling. Like, how does it work with the directional scattering of photons? How should I think about this? Like, that it's like not just going into arbitrary directions.
Yes,
but
that's a very good question. That's what actually, when I first kind of came up with this idea, what I was by far the most worried about. And then I looked a little bit into this. There's a lot of old work where they say, okay, we have that and that strong superradiance, and it becomes such and such directional, okay? And of course, if it's perfectly correct directional, it doesn't work anymore. Because first of all, because the directionality, you need that in order to kind of average out to the right direction, but it also has to do with entropy, right? So you don't have this entropy anymore if it really goes only in one direction. Turns out that for the kind of strengths of superradiance that we are looking here, it gets somewhat directional, but only mildly so you don't need to worry about this. But yeah, good question.
I just had a quick question about the molecular cooling as well.
Uh-huh.
So you said they use a 6-photon transition to make sure things are closed, but you could build a closed thing with 4 photons. So I'm wondering why you need 6 rather than.
But the point is, you are right. We did that just for simplicity in this case, right? Because with the 4s, you would have to really see which one do you use. That means you would have to add on 1 to one of these. But the thing is, with the 6, you can take the same transitions and always have a delta J equals to 1. That's why we use 6.
Great. One last question.
I just had also a quick question about the molecular cooling, just the experimental parameters that you need. I mean, you said you need the optical thickness on the vibrational transition, which one can get at 10 to the 9. But how about the optical thickness on the EIT condition? Is this necessary, or is it? No,
it actually should not be. And for example, in the case that we have, where we have, I mean, an optical transition in a 10 to the 9 is not dense, and we definitely don't want it dense. So you really want to get at the point where it's dense, optically dense for the vibrational transition, but optically dilute for the other transition. Because there is, I have done this long enough. In a really optical dense EIT transition, there are so many problems. Don't even try. Okay.
Oh, great. So let's land.
Thank you.
We have our last speaker of this morning. Okay, so we have Simon Colombo. He will speak on behalf of Vladan, and he's going to tell us about light-induced ortho-low interactions for quantum metrology with atoms.
Okay, great. Thank you for the introduction. So, as Anna Maria said, I'm here in place of Vladan that couldn't come. And I'm going to tell you about how we're trying to use and control all-to-all interactions in atom for applications in quantum metrology. So we'll start by thanking everyone that worked on this project. It's kind of a long-standing project. We already are starting the 3rd generation of grad student. Some of them are here and they just graduated. And I also put our nearest neighbor in lab. It's where basically we jump in when we need some mirrors, some glasses, something that we don't have in our lab, but also because there is some interesting fact that has been observed there. It's an excursus, so it's a Rydberg lab, and what you have to know here is that at some point we had to load as many as possible rubidium atom in a dipole trap, and to do that, since now there is machine learning, AI, and everything, we try to implement to tell a computer to optimize parameters for loading from mod to the dipole trap in the best possible way. We went for lunch. When we came back, we got a PC. It's a small one. It's just kind of 200 atoms, but it was kind of interesting that we observed something like this, that the computer could find a BC just by loading atom in a dipole trap. But there is also a part of, let's say, humanity in this discovery. It's that actually when we aligned everything, we didn't do a good job. So the dipole trap was kind of, the beam coming out down here was kind of clipped, and so it was creating some dimple in the focus here. And actually when the computer was trying to optimize the atom number, at some point it could get enough atoms that there was some condensate. So that just to say that apparently AI is useful to optimize everything, but grad student and postdocs will be always useful, especially if they do happy mistakes. So, okay. And this also, it's anyway some kind of light-induced stuff, so it's related with my talk. So now we'll go back to the main topic. I'll start with the outline. Just very general what atomic sensors are and what is a quantum metrologist, just to give a kind of overlook. Then I will speak about entanglement on an Ethereum optical clock that we did in our lab. That's our first application. And then I will introduce a new paradigm that we investigate experimentally. And I will give you more details, of course, later. So let's start. Atomic sensors in general can be considered as just a spin 1/2 atom system, just to simplify the things. And what we're trying to do is to measure the separation in energy. And this separation in energy depends on some parameters that we want to measure. And we can split our protocol in 3 steps. What I show here is a Ramsey protocol. We prepare atomic state, we let the state evolve, and then we measure the final state. At the end, the phase that it's accumulated here is just proportional to the difference between our local oscillator and the actual frequency related to the energy separation between the 2 levels. If we do this with a single atom, that creates some problems, because when we try to measure our final state, we can get just 2 outcomes. Or the atom is measured spin up, or is measured spin down. So at the end, you have an uncertainty in your phase that's pretty large. It's 1 radians. So what we do, not everyone does, usually use many 2-level atom system, and this can be mapped to a spin and half system. And here it appears a new kind of Bloch sphere. That's a generalized Bloch sphere, where the collective state of the atom is represented in this case by this blob here, which is a coherent state here, and it's just the Wigner function of this thing. In that case, then when we perform our measurement, our sensitivity is limited by the width of the projection of this blob here, which is going with 1/√n. If we can reach a sensitivity that's like this, that's a so-called standard quantum limit, that you cannot go beyond that if you don't use quantum entanglement or quantum correlations within the atoms. So actually a better picture of the protocol is basically when we use this generalized Bloch sphere, when we have said the state is a collective state, the phase is accumulated, and we measure the final state. That's the projection. So atomic sensors, there are many kinds of them. There are magnetometers, where they measure magnetic fields. And if you use atoms, you have 10 to the 10, 10 to the 11 atoms. So it's a pretty large number, so your uncertainty that goes with 1/√n, it's pretty small. But if you use some artificial atom, like NV centers, you can go down to single spin. So at some point, you may be limited by projection noise. You can have electric field meters, where they use kind of the same number of atoms as here. You can have gravimeter, atom interferometers, where the numbers start to decay to 10 to the 6. And then you have optical clocks that are ideally sensitive to nothing. So that's the splitting, so that you measure time. And you usually have between 1 to 10,000 atoms. 1 when you're using ions, 10,000 when you have a nice optical lattice trap. And why you cannot put many more atoms is because these devices are pretty sensitive. And if you have too many atoms, they start to collide, and then you have effects that you do not want to have if you're trying to do metrology. You may want if you're trying to understand how a many-body quantum system works. So, of course, improving metrology can have a huge impact and opens up many new opportunities, both in applied stuff like just defining time standard, for example, or navigation and localization, but also it can allow you to observe in how it works our world with new eyes. Here's just a couple of examples. So, and now I will introduce very rapidly quantum metrology. This is what you can do if you prepare your state to the best of your capacity. So you're limited by the standard quantum limit, but if before starting your sensing time, you generate some entanglement within the atoms, you can actually create a state that's potentially more sensitive to phase changes than a coherent state. And to do this, you need your atoms to evolve under a nonlinear Hamiltonian, basically get atom-atom interaction, so that you can generate this collective entangled state. This is a squeeze state, what I'm representing here, but you can generate any kind of state you would like to have. Of course, this requires atom-atom interaction. But as I kind of said before, when you're doing sensing, you don't want to have any atom-atom interaction. So we need some switch. We need to be able to turn on demand the interaction and turn it off when we don't want to use it. And well, it's kind of intuitive that if you want to switch on and off something, the first thing you think of is light. So it may be nice if we could generate atom-atom interactions that are light mediated. And in our lab, we do that by putting atoms in a cavity, because in that case, then the atom-light interaction, it's pretty large, and so it's also easy to get a atom-atom interaction. And everything with the goal to go below that limit here. Okay. So the system in our case, as I mentioned, is an ytterbium optical clock. We use ytterbium 171 atoms. We usually load between 100 to 10,000 atoms, depending a little bit on the experiment we are doing. And this is roughly our experiment. Atoms are loaded and coupled to a cavity mode. And the question is why we use ytterbium. Well, it has an interesting optical clock transition. It's 7 milliards. It's very narrow. It has a Q factor that exceeds 10 to the 15. And in recent experiment, not in our lab, but actually they could reach kind of fantastic stabilities that are essentially limited by the projection noise. So in that case, in this kind of platform is one of the state-of-the-art platform for detecting very small signals, and it also reached the standard quantum limit. Another interesting feature.
Is that a fermion version?
It's a fermion, yes. It's a fermion version. Yes, it's a fermion, and since it's a fermion, it has actually a nice feature. It's that for ytterbium 171, we have a ground state that is a spin one-half system. So everything is simple there, and you can use this as a nice playground for quantum mechanics. There is this transition that has a line width of 200 kilohertz, which is not good for optical clocks, but it's still pretty narrow. And what is really important here is that the ground state is a nuclear spin. So you apply a strong magnetic field, you have a very small Zeeman splitting. In our case, we apply 14 Gauss, and we get a splitting of 10 kilohertz. So it's 1.4 millitesla, 10 kilohertz. While in this transition here, it's mostly electronic spin. The splitting is going to be 20 megahertz. So, and it's much larger than the gamma. So actually, we have an effectively closed transition. We can think about our system as effectively a spin, three-level system, and we can use this one to perform many things. And what we do, for example, is, well, we move S and P, but to give space for a cavity, we tune our cavity to be resonant with this transition. And what happens when we have a cavity that's resonant with a transition like this, we scan the laser through the cavity, the laser frequency. Here, what we observe, it's a Rabi splitting, basically the 2 mode. And the splitting here is proportional to the number of atoms that are in the spin-up state. So we can use this scan, this splitting, to get information about the collective atomic state. This is how we measure the projection of our state at the end in the ground state, the projection along Z. So this is how we measure, that's interesting. But we want to generate also entanglement. And we do this using the same apparatus. We have atoms in the cavity. And what we try to do first is to generate one axis statistic Hamiltonian. That's basically just a Hamiltonian that depends on SZ square. SZ is the collective SZ operator that can also be seen in this form, where you notice that there is an all-to-all interaction. Every atom in the ensemble interacts in the same way with all other atoms. So the question is how we generate this. So we can have an intuitive understanding. If we send the light that's slightly detuned from the atomic transition, the light goes into the cavity. It's non-zero around here, the probability that light goes into the cavity. When there is light in the cavity, atom sees a light that's detuned from their transition, right? So they will experience a light shift. That's what I see here. If they experience a light shift, that's like a magnetic light Hamiltonian that's proportional to the intensity of the light inside the cavity. So it's proportional to the number of photons that enters the cavity. And then there is a cavity that does the magic here. The intensity is proportional to SZ, to the collective SZ state. This can be seen, for example, on the Rabi peak. If you are slightly detuned here, you can see that when you have a little bit more atoms in the spin-up state, so you have a larger SZ value, there is more light. The split thing opens up, so there is more light entering the cavity. So this means that actually the atoms inside the cavity will feel a magnetic field that's effective magnetic field that's proportional to the SZ itself of the ensemble itself. So if they are a little bit above the equator, they experience a positive rotation. If they're below the equator, they experience a negative direction. So this will just induce a shearing force. And if you shear a circle, you will get an ellipse. And this you get a squeeze state. And if we zoom in and we remove the Bloch-Sphere curvature and everything, basically you end up with a state like that. So the question is how, first of all, do we see if there is any squeezing? Because with this kind of Hamiltonian, it's not changing any value on SZ. So if you just generate squeezing, the shearing, and then we measure the variance along the SZ, so we repeat the experiment many times, we will just observe the same variance as the standard quantum limit, which gives you 1 if you normalize it correctly. But what we do, we apply a rotation. It's in the ground state, so we rotate, we get squeezing because the thing is aligned in the right direction. And then at some point, we see also the anti-squeezing. We put this state vertical, and it's easy to rotate because here we are within the 2 Zeeman sublevel in the ground state, and it's just a 10 kilohertz RF field that anyone can produce with the right coils. Of course, when we do this, we are limited anyway by the measurement resolution of our system. We are not able to detect every single atom, we just see the collective state, and also we are not able to resolve any single DQ level, so we cannot count SZ without uncertainty. There is some uncertainty, and this is our limitation that we have here. So we apply this to our system, and here we generate the squeezing with this technique within the 2 Zeeman sublevels in the ground state, which is nice and interesting, but it's also maybe not so smart because this is effectively a magnetometer that is almost not sensitive to magnetic field. So it's not very smart, but we wanted to have actually a squeezing on the clock transition. So the idea that we have is that, we read in some paper, actually, is that you generate the squeezing here, and then with a coherent pi pulse in the right direction, you can transfer one of the population in the clocked transition and then actually effectively mapping the squeezing from the ground state to the excited state. So here are the results when we did the squeezing on the ground state. we observe is the tomography of our state. The rotation is shown in logarithmic scale because this tip is pretty narrow, so it's much easier to see it if we do it on logarithmic scale. So we observe a squeezing, and we observe also some anti-squeezing appearing up here. So in the ground state it works. Then we transfer everything. We first need to see if we can transfer the population in a coherent way from the ground state to the excited state, and then eventually bring them back. That's what we tested here. This is basically just a Rabi spectroscopy on the clock transition, and here it's a Rabi flopping. We can transfer up to 90 to 93% of atoms coherently in the clock transition and then bring them back in the ground state. So we did that. We transferred the atom in the clock transition. We transferred them back, and then we detect in the ground state because it's easier, and the coherence time here is infinitely long for our experiment. And what we observe is that actually the profile of the tomography is unchanged. If we transfer the atoms up and down from the clock transition, or we just observe the atoms directly in the ground state, there is no change. So this means that this process is at least not introducing any extra noise, which is good. Of course, we have to test if we still have, for example, if this squeezing can stay there for a long time. So what we did here, we generated our squeezing, we put it horizontal. Horizontal in the Bloch sphere means that we are not sensitive to phase, so we are not sensitive to a very bad optical clock that we actually had. And we transfer the squeeze state on the clock transition. We wait there for long enough, for some time, up to, well, I think 500 milliseconds is the longest we tried. And then we bring them back and measure the variance. So this, basically the variance remains below the standard quantum limit. Is a solid circle forever, in our, at least up to 1 second. But if you consider the contrast, we see that there is a contrast loss. So the actual metrological gain that we can get, it's a bit less. It's the open square data here. It stays below the standard quantum limit, which is 1 here, for more or less 200 milliseconds. Then it kicks up, but it's still below what you could do if you start everything with a coherent state, and then you consider the contrast loss also there. So this for us was enough to say, well, the entanglement, so the squeezing, survived long enough on the clock transition so that could be used for real clock applications. So we tried to do that. Unfortunately, we had a bad clock and a bad optical clock. I can tell you the little bit the story why. So here you can notice that's maybe 10 to the minus 13, the stability. And this is not the full clock operation. I will specify it later. While good people with clocks can get a fractional stability in 10 to the minus 17 per root hertz or lower. The issue is that we have our lab, we have our clock, laser. We did all the things as good as we could, and then we have fibers, right? Going from one table to another, coming back, and so on. And at some point, we had some visitor from NIST, I guess, and we asked, "Oh, but are you are you stabilizing your fibers?" Say, "No, there is no need for that." Say, "Okay, so let's take the measurements." So we took all the measurements, and well, it's really bad. So we were a little bit unhappy with how we were locking the laser with ultra-stable cavity. Well, it turns out that when we asked these questions, the other person thought that we were speaking about maybe half a meter or 1 meter of fiber, but actually we have something like in total 30 meters or more fibers. So we had to do fiber stabilization, but we didn't, and so that's why we have a very bad clock. But nevertheless, when we measure everything, we try to do our experiment and run the clock with a coherent state, so it's blue data here, and with a squeeze state as input. After we removed all the local oscillator noise that it was there, so we could characterize it because we could measure the noise from the local oscillator, we could remove that component. We could see that actually we observe squeezing below the standard quantum limit of 4.4 dB. This is the contribution coming only from the atoms. It's not the squeezing on the clock. May look not a lot. I mean, if with a good clock, you could get this improvement. It may look not a lot because actually 4.4 is 2.8. But it means that you need actually, you can integrate, you can reach certain stability, precision in your measurement 2.8 times faster. Which, if you compare it to your salary, if you multiply it by 2.8 your salary, you may change the perspective and work. Or also in the opposite direction.
So what is being plotted? Is it delta mu over nu on the vertical axis?
Yes. Yes, sorry. That's a fractional. Yeah, I think I put a white square to remove something. And Yes. And at the end, everything was limited by our final state readout. So now I will introduce you a new paradigm that we experimentally demonstrated and used and developed a little bit. And on this case, all the experiments are done just on the ground state of, so in this, within the 2 Siemens of levels. So no optical clocks so far, but maybe applied later. So now we'll have a little bit of small cartoon. So remember, the improvement is limited by the final state readout. So in general, sensor performance is characterized by its signal-to-noise ratio. Here I have some two cars in New York and Manhattan, actually, and I want to target one of these cars. And I'm using a very bad GPS, so I cannot see the 2 cars. One way to identify where is my car is to reduce the noise. That's what you do when you do spin squeezing. You reduce the noise, so your signal-to-noise ratio increases. It's great. But is that the only way to improve the signal-to-noise ratio? Well, it's not. And to demonstrate this one, you should move here in Boston, where they build streets in a very highly nonlinear way. So, and you have an alternative now here. You can try to improve the sensitivity of your GPS, or you just wait a moment and let the system evolve under this nonlinear Hamiltonian. And actually, you will see the 2 cars that one ends up going towards Seattle and the other one ends up in Logan. So you wait a little bit and you let the system evolve under this nonlinear Hamiltonian, and you can actually distinguish where the 2 cars are. Okay? So in that case, I increase the signal and I increase the signal-to-noise ratio. Now there is a problem, because all I could hear was classical noise, just our readout noise, for example. But if my limitation is quantum noise, this is why I have a cat, but I think I'm better than Heisenberg because it's not going to die, this one. It's just the localized on Many Street. If I let the system evolve under this nonlinear Hamiltonian, I have the 2 cars slightly split out. They will end up basically being delocalized everywhere, so there is a huge increase of the spread of this car, right? So the noise increases a lot. And that's not a surprise, because when you do quantum mechanics and you have some unitary evolution, if 2 states have a certain overlap at the beginning, you let them evolve under this unitary evolution, the overlap stays the same. So the question is, can I use this amplification in quantum mechanics? If we go and look at something a bit more realistic, the answer will be yes. And so if I have something classical, and I have just my SZ square Hamiltonian as I had before, it's a nonlinear Hamiltonian, I have a certain displacement delta. If I let the system evolve a little bit, I will get a displacement at some point that it's larger than delta, and this is what we saw earlier, so I can amplify my signal somehow. In quantum mechanics, it doesn't work very well, because even if I have an improvement in the signal in this direction, my noise increases also a lot. But if I can reverse the time in my system after I introduce the signal, actually I can get I can amplify this signal a lot, and I can get basically the same noise here, but a larger signal. So I could increase the signal-to-noise ratio by reversing the time of my system. Reversing the time of my system is a cool way of saying I'm just changing the sign of the Hamiltonian. So the question is then, how can I reverse the sign of my Hamiltonian in my system in an easy way? So in my systems, remember, are just atoms inside the cavity, and when there is light on, they evolve under this nonlinear Hamiltonian. This is the sketch we had before. It's a light shift, and I get a certain shearing. If I detune the light on the opposite side, I can have the intensity being always proportional to the SZ, but have a light shift that has the opposite sign. And so in this case, I will shear in the opposite direction. So shearing in the opposite direction is basically just putting a minus in front of the Hamiltonian, and I can actually undo my revolution. And this is the experiment, finally. We start with a coherent state. We measure, we apply a pi half pulse, and we measure actually the Z projection. But if we remove the pi half pulse, it's just equivalent to measuring just SY direction. That's, in this case, we just measure the SY direction, so the horizontal projection. Nice and Gaussian. We let the system evolve under this SZ square Hamiltonian, and we see that the noise grows, still grow, it grows, and at some point it starts to wrap around the generalized Bloch sphere, so we cannot have a spin vector that changes in value. So it wraps around, it starts to look non-Gaussian anymore, and actually at some point you have something that is kind of completely wrap around the Bloch sphere, so you get a distribution like this one. And then what we do, we say, okay, now let's change the frequency of the light, let's detune the light on the other direction and let the system evolve backwards in time. And we can recover from this state, we can go back to our Gaussian distribution again, nearly limited by the coherent state size, so the standard quantum limit. It's a little bit wider, it's just a factor of 2 invariance larger because our system is not perfectly closed, so there is some losses, but that's kind of working. At least in terms of noise, we can reduce the noise. So one can always argue, yes, but where is the signal here? And can also, I mean, one way of getting some Gaussian distribution is to thermalize everything. So to show that it's not the case, we do the same process, we evolve forwards in time, then you introduce a signal, and then evolve backwards in time. In that case, we were interested then in the mean point because we know that the noise goes back to the coherent state. So here we measure the expectation value of Sy, I mean the average Sy measurement that we obtain divided by Sz, as a function of the rotation that we put inside. So the black lines represent the standard, the best you can do with a Ram's interferometer. If you introduce a rotation of 0.1 radians, you will observe a Moster rotation of 0.1 in the right direction. And here we see then our signal is clearly amplified by a decent factor. Here is amplified by 3, 4, it goes up to 5 times larger. And then at some point we will have losses and everything starts to shrink and so on, but there is some amplification. So in that case, then we can define our metrological gain. That is just the amplification square divided by the normalized variance. If you get 1, you basically sit on this purple line, which means that you have the same sensitivity as the standard quantum limit. And this, of course, it changes for atom number, but here we look at different atom numbers, how much we can improve. Here, the red data are our data here. We see that by increasing the atom number, the gain that we can get beyond the standard quantum limit improves with an Heisenberg scaling, so improves with the number of atoms proportionally. So we're sitting kind of 12.6 dB away from the Heisenberg limit, and at most we could load 430 atoms in average in our system and get an improvement of 13 dB. 13 dB is 20 times better, the rotation. And here, just we compare this data with not all, but a good fraction of squeezing that has been performed, or actually entanglement that has been performed in many body systems to improve metrology. So we have blue are BC's experiments, where you have SZ square interaction for free. It's hard to turn it off, but you can. Red data are ultra cold atoms but still thermal. Some of them it's even hot. And here is the regular holder where they could get 17 dB actually with 1 million of atoms. And grayish data here, dark one are ions. These are single ion chains. They got some nice GSZ state. This one is, I think, John Bollinger. It's a very similar system, mathematically at least very similar to ours with ions. And here it's a tweezer array of neutral atoms. So this is interesting because you can extrapolate and you could get quite good improvement in new sensitivity. And what we try to do is, let's see if we can improve the sensitivity of our very bad magnetometer. So we try to be phase sensitive in this case. We create our squeeze state or highly entangled state, put it vertical to be sensitive to phase, and measure. So the standard quantum limit stays on the standard quantum limit, that's great. And when we did it with our protocol, we got an improvement of factor of 15. And in this case, it's too obvious if I tell you that's 15, it's a lot for your salary. So I can tell you if you need to measure something with a certain accuracy and you need 60 years to do that, it's a whole life project. Well, with this improvement in integration time, it's just a PhD project. So things can become more interesting. And, well, we try to go a little bit further and try to generate entanglement exponentially fast, because with this method, with the time reversal, we see that we can actually have a huge improvement. But to generate this kind of entanglement, usually you need to wait longer and longer so that the system evolves. So it would be nice if there is something that evolves exponentially fast, so you don't have to wait too long to reach a very highly entangled state. And the trick to do that in our system is just to add a global rotation. It's very much similar to, we use the Lipkin-Meshkov-Glick Hamiltonian in this case. It's very much this analogous to, I think, transverse Ising model. And in that case, the dynamics changes completely. For certain parameters, there is this point here, which reminds of Boston. But if you look at it classically, it's a saddle point. It's actually the inverted pendulum. And classically, so if you have a small displacement along these two lines, actually these 2 points goes away exponentially fast. So we try to do it with our quantum system. We just put our coherent state on this crossing point here. And we see that what it should happen is that it generates entanglement exponentially fast. We get squeezing, but since our detection is not so good to detect all this small feature and so on, what we did, we let the system evolve. We know how to reverse, we introduce the signal, and then we know how to reverse this Hamiltonian, because as this square we are able to reverse. To reverse the rotation is quite easy, you just rotate in the other direction. And so we could detect metrological gain in this system that grows exponentially fast. Here is the gain we got versus the time we expose the system to this nonlinear Hamiltonian. Of course, this is in dB scale, that's why we have a line. And at the end, basically, this is two experiments. One when we didn't apply any displacement, any signal. One with displacement signal, we could reconstruct our Wigner function and look at the overlap. So I will reach the end with a summary. So light-induced all-to-all interactions are a good resource for quantum metrology, especially if you can control it well, because you can turn it off. So we demonstrated that you can generate metrologically useful entangled state in optical clocks using this technique. In our case, the performance at the end were limited by the local oscillator noise and by the projection noise of our measurement. And now I think I may have convinced you that this new paradigm, where we can reverse the nonlinear evolution, is kind of appealing because it's quite robust. It allows you to get a lot of improvement, and actually it renders maybe many other scrambling Hamiltonian that generate entanglement in a very weird way maybe, but exponentially fast. It could be useful and used also for metrology. And of course, the outlook is, well, we use this technique on optical clocks. Thank you.
Excellent. Thank you for the great talk. We are open for questions. Maybe let me start. Yes. So the Ising Hamiltonian is particularly tolerant to the noise that, I mean, if you don't have any spin flips, then you can get 1/n, even with decoherence and with superradiance, but, or light decay from the cavity. But when you go and you introduce the rotation, you become much more, even though you are exponentially fast, you get much more 1/√of NC instead of NC. So do you think that you can win then, or why? What is the gain there?
Yes. That's true. That's one of the reasons why here I cut. Actually, the things are going down later in this result here. We have a way to optimize it, but to really win over the overall possible gain that you can get using this Hamiltonian, so the Ising one, or the as square Hamiltonian, in the ideal case is not clear. Actually, I think the as square Hamiltonian is simple. One-axis twisting, if you have a perfect thing, you can reach a GSZ state. Mm-hmm. With this one, no. You need a two-axis twisting. So. Okay. But here you may win in terms of speed.
Okay. Mm-hmm. Suzanne?
So if you could choose any Hamiltonian that you wanted, when somebody tells you, okay, I give you a time reversal tool,
Yes.
what would you do?
We'll just try it directly here.
Again?
I will do this protocol. Just evolve it, get something.
No, but what Hamiltonian?
Oh, which one? Oh, anyone. Oh. That's a good question. I don't know. I would start first of all with, let's say, why not SZ4? Why not? I mean, just simple stuff. Actually, I would use maybe also two-axis twisting. SZ square plus SX square. This is exponentially fast.
Just to clarify, like, am I understanding right? Maybe like following up to Susanne's question. So the Hamiltonian that you want instability in your Hamiltonian, right? So that's actually where you see exponential scrambling. That's connection there. So you actually want like instability in your Hamiltonian when you're choosing.
Yeah. Yes. Instability in metrology can be called as sensitivity. Yeah, no, I mean, that's not obvious. I mean, if you think in that way, you can see if something is unstable, it's actually very sensitive to perturbation, which, yeah.
More questions?
No, there's one up there.
Okay.
Sorry, thanks. Hi, great talk. I was wondering if you fix the local oscillator noise, what would be your limit for squeezing with a cavity? And what would be limited by?
Okay. Well, just squeezing is our measurement resolution. If we have a perfect measurement resolution, then you'll be limited by the curvature of the block sphere. So this means that you will continue to squeeze, and you have two effects. One is you start to wrap around the block. I mean, both you wrap around the block sphere, so your signal decreases because actually your mean point is not anymore rotating on the block sphere surface. And another effect is that when you look at the projection along the squeeze direction, you will not have anymore a Gaussian distribution with a narrow thing. You have a narrow peak with some tails. So you would need to use some more fancy way to extract all the information, which is not just the variance. Yes. If not, if you do the time reversal, then in that case, it's very much the same limitation, the block sphere curvature, but it kicks in much later.
Yeah, hi. I have a question regards you're saying that this is a cavity that you can turn the interaction on and off, right? And by sending the light or not. So how about the atoms interact with the vacuum mode of the cavity? That should be also very strong, right?
Much less than when there is light.
Yeah, but averagely the intra-cavity photon is not very large, right? So what's the difference between square root 0 plus 1, which is the vacuum, or square root, for example, 5 photons in the cavity, 5 plus 1, which is square root 6, is not much different.
Okay, trying to think how to answer that. And one way of saying this is that you couple your atoms with the cavity field, that's a bosonic field, right? And when you send in photons, you're actually driving your bosonic field. Right, and so this grows much faster than when you're not driving it. I don't know the numbers, but that's the way. There is a possibility to generate squeezing with vacuum only, but just too late for them. Yes, yes.
Excellent. So I think we are ready for lunch. So let's thank the speaker.
Thank you.
Yeah, lunch will again be served in the library again, and then distribute around. Again, the rooftop, I think today is a good option.
And please don't leave personal items.
Oh, no, that's it.
No,
Yes.
You will see, maybe not, but you're going to see the measure.
I see what you're referring to. Yeah, I know the John's paper, right?
Yes, exactly.
We didn't try it, but I think we can.
But seems that because in our case, we were limited by the scattering, but I don't see you are doing, in our case, because it's N gamma, you can investigating, it was very bad, but it seems that you are not very limited.
We can optimize it. That's probably, yeah, that's very interesting.
Because just by this way, to measure fidelity, it's a way that you can detect the cat state without, or give an indication of the cat state without doing an actual measure.
Oh, okay.
So
That's
to
interesting.
measure the I naught, the zero
Okay,
computation.
yes, no, I can tell you. To reach the cat state, we can do that only with 10 atoms.
Yeah,
Because
yes.
we're not able to put 10 atoms in. But with a better cavity, yes.
No, I'm not going to very long, but I think the subcats
Okay, the kitten, yes. Okay, yeah, that's true.
much
Yes.
faster, and they manifest in some peaks of the I naught, so you might be able to see this
Yeah,
what
that
I'm
would be
talking about
cool.
is the fragmentation
Okay.
of the noise distribution, and yes, all the way to you see the cat state. And
Yes,
then you go
that's so.
back.
Okay.
Beyond
Yeah, that's
squeezing,
yeah,
and-
yes, yeah, no, that's good. That's interesting. We thought about at some point maybe we can see some kitten state, but we were too naive and we say okay, we just measured the distribution, which
That's
is the hardest way.
exactly. So that's what it will
So
measure
maybe
the
should we
I
do
naught.
okay?
Then you should see the structure of the I naught. I mean, they start from zero, then you grow because of the squeezing, and then you start to have this decrease and all the dips that are
Okay, yeah. Is that critical that you have a fixed Newton number? Or you think, because I guess that's just the phase interference, right? And then
well, I mean, you are saying fluctuations of the atom number from shot to shot.
yes, we do have some.
Yeah, but
It's 10%. We can reduce
I
it.
think we
but-
can. Yes, it would be determined how much you are going to watch.
Oh, the kid. Okay, exactly. It's not a dicky thing. So okay, yeah, I think it's possible then. That'd be cool. Yes.
Yeah, so I think you take the Fourier transform and you take the DC component of the
Yes.
Fourier transform and the integral over all angles. You have to do
But it worked pretty
the,
well.
you have to integrate over the signal over all angles, and then this I naught will tell you this information.
Okay. Yes, we didn't do it, but I think we can do it.
Okay, that would
Definitely.
be
Thank you.
great.
Yes. Thank you.
Very helpful. Thank you so much.
Thanks.
That's really, yeah, interesting stuff.
Thanks.
I was actually wondering, like, could you imagine that there are ways, because now as Anna Maria said, like there is like dissipation, which in general is bad every time you do stuff like boundary observables. Could you imagine a scheme where actually this could happen? So you would have like a shrinking or a changing
You would have to go back into it.
scramble more due to that?
What time scale is
I
this?
don't know.
What length scale is this? Actually, I thought the
I mean, the time reversal is not trivial as well, right? So
No,
yeah.
exactly. No, time reversal is not trivial.
Yeah.
But
I can tell you, I mean, yes, and that's actually it's a very good idea. That's actually
yeah, I don't know. I mean, the usual thing we do is, well, if you want to have less losses, you just want to enhance the cooperativity in the atom, single atom, and the cavity volume. And that helps. But that of course is a big because of the cavity vacuum noise. You don't want to change the cavity if it works.
Yeah. So should we head down to the library?
Okay. See you later.
You will say right here?
Yes,
But you can also go for lunch.
Yes. Oh, there's lunch here?
There's lunch here, yeah. Already here. Yeah, so you can go there.
And of course, at the end, you rather want it a little bit smaller than one, which means you lose more, but whatever you have left should be more. But this is, I mean, if you take spatial into account, it's a great department. If you calculate it with let's say, assuming you have a single mode and you calculate it within a single mode, it's actually should be able